Okay, welcome everyone. Does the sound okay? Thank you. We have a pretty tight schedule, so I'm going to try and keep to it and get right to it. So it's a pleasure to introduce Anima, who is my co-organizer of this meeting, and she's going to give a first talk about AI accelerating science and the use of neural operator on function space.
Thank you, Andrew, and welcome to the first of the many AI4Science workshops this year and in the coming years. It's great to be back in person after, the break during the pandemic where we did do some virtual sessions, but now with both virtual as well as in person, I hope we can continue to grow the community here and look at how AI impacts all areas of sciences. And also, more importantly, what are components of algorithmic design in AI that current algorithms don't fully fulfill with respect to scientific domains, right? So what are some requirements in the scientific domains that are not easily fulfilled, that are challenging for AI? And so that's the virtuous cycle that here at Caltech we are very interested to explore and to ask, how AI informs science, science informs AI, and we see that cycle. To motivate you in terms of why AI is necessary in so many scientific domains, right? Especially the theme of this workshop is how does AI help in accelerating scientific simulations? Let me give you an example by my colleague Tapio Schneider, who will in fact be delving into climate sciences in the afternoon. But one of his projections is in terms of the computational requirement for getting very precise climate simulations. And that entails simulating these, what we call low-lying clouds or stratocumulus clouds. And what that requires is going to very fine scales, right? And that's something that is different from standard computer vision or other applications, where you're going from pixels and trying to summarize it into objects or something low-dimensional. On the other hand, with so many of these scientific domains, the fine scales matter a lot. If you want to ask, will there be a hurricane 2 weeks from now? If you look at the image of the winds today, you can't see anything, right? So it's not something that is a visual feature. It's not something that is just in the coarse scales, but you have information embedded in the finest of scales. And that's what makes it extremely challenging and different from standard computer vision and other application domains we see with AI. And so in this case, what you need, ideally, right, in the ideal world to remove the biggest source of uncertainty in these climate simulations, you need to be able to go to a spatial resolution of 1 meter across the planet. So you embed points 1 meter apart all across the globe. And you simulate it at also forward in time at 1 second or even less. And so you're doing very fine, refined simulations. And that is expensive. And in fact, it's so expensive that it requires about 100 billion times more computing than what we have today, according to estimates by Tapio. Right? And so that's a challenge for AI. So can AI help us accelerate some of this? And if so, how? And what are principled ways to do it, while also respecting the physics that is necessary to predict climate of the future, which is unknown. So these are the challenges that are posed to AI. And that is only one such application of climate simulations. It's also the case if you want to go down to the finest scales of molecular properties. So how do we simulate quantum chemistry, right? The Schrodinger's equation is the basic equation that governs all the interactions between atoms, between molecules, and also extremely expensive to simulate. And so given these multitude of applications that require such heavy computational loads, what can AI do? So first of all, we have here a hierarchy of accelerations. right? So if you think about how single-threaded computing or CPU cores, how that is getting faster every year, the Moore's law is plateauing. So it's no longer doubling every year or so like it used to in the past. And so that's where accelerated computing like GPUs have become a lot more important, and especially in AI, right, with heavy computational loads, we see that GPUs are almost a necessity. But on the top of it, you also need to scale up and out. We are building bigger and bigger supercomputers today. And those supercomputers are hybrid. They're a mix of both AI and what we call HPC, or traditional scientific computing workloads. And we are in this exascale era. So we're building now with not only thousands of GPUs, but tens of thousands of GPUs now in the latest supercomputer. But even all that computing in the world is not enough, right? And that's where machine learning, if it were to sit on top of the acceleration and supercomputing scale equipment, what machine learning will provide is the ability to further accelerate by orders of magnitude. So that's the hope, right? Now the question is that possible, and if so, how do we go about designing it in a principled manner? And that's where this framework of neural operators has been very effective in being able to design effective surrogates for scientific simulations and other what we call learning on function spaces. So before I get into the details of how we went about it, I do want to celebrate a vast group of collaborators and core contributors to this project. This project started out as an interdisciplinary collaboration with Andrew Stuart, with Kaushik Bhattacharya, and students and postdocs in all our groups sitting together and exchanging ideas, right? So that's one thing about Caltech, is its small size really helps us nurture these ideas and think about many different disciplines coming together and asking how we can bring those ideas together. And since that initial work, it has expanded to so many other collaborations, many in the application domains. You'll hear from many of them in the afternoon. There's also Zach Ross, who will talk about it from seismology applications. And as you can see, students and postdocs, both graduate and undergraduate students, working here at Caltech on these range of problems in neural operators. And not only that, we have an expansive network of collaborators at many different organizations. As you can see at NVIDIA, there is a large group of both research scientists as well as engineers who are helping us build open source libraries, helping us scale on supercomputing level of compute for many of these problems, including weather models, as I'll show you in a minute. And as well as many other national labs, like Argonne National Lab, Lawrence Berkeley Lab. And I think building these collaborations is really essential to me, because there needs to be deep understanding of the domains, right? There needs to be deep understanding of the current methods for simulations, the numerical methods for solving them, as well as deep understanding of AI. So bringing all this together has been our mission here, and it's great to see how much this has grown in the last few years. So with that, I want to now delve into neural operators and ask, how is that different from many neural networks you would have seen? You've certainly seen transformers. They're everywhere. ChatGPT is every day in the news, right? They're built on transformers. There are the convolutional neural networks for computer vision. So we have all these various neural network architectures. So why not just use them for building surrogates for scientific simulations? Why do we need a new framework? And so that's where this notion of discretization invariant learning comes in. So if you take any of your favorite neural network architectures, right, Now, and let's say you train on images at a certain resolution. As you see, the images, when you put into training a neural network in the standard case, is always at one resolution. And then you also test at the same resolution. So if you try to test it at a different resolution, most of the time you can't even have that as a valid input. And let's say you try to interpolate and make it a valid input. Even then, the performance is usually very much degraded. And so that's why we cannot use many of these standard neural networks into building surrogates for scientific simulations. And so what people have done in the past instead is to take an existing solver, right, get solutions at a coarse grid, and then try to do super resolution on top with deep learning. So those have been the attempts in the past. But to me, that's limiting and it's rigid because you assume you always have a solver and it's giving you solutions at one fixed resolution. And you're doing super resolution only to another resolution. And by doing this, you can never be guaranteed to completely learn in a generalizable manner unless you pick the coarse and fine scales in the right manner. And that's what Andrew will talk about in his next talk, how the theory may now allow you to design it by picking at appropriate scales. But if you're not aware how to do it, right, this trying to decouple between having a solver and deep learning on top may not give you that flexibility. So instead, the approach I want to ask is, what if I want to replace completely the existing solver and use a neural approach instead? How can I go about doing this? As we can see, with standard neural networks, we cannot hope to be able to do that effectively, right? Because what we really require is not just the ability to feed in data at one resolution, but to feed in inputs at any arbitrary resolution. And not even necessarily a fixed grid, right? It can be like, or rather uniform grid. It can be now all kinds of irregular or even adaptive grids. So these are abilities that many of our numerical solvers have. And so we need to be able to have similar flexibility with a neural approach if we hope to completely replace those solvers with a deep learning approach. And so that's why having these existing frameworks is limiting. And so the other aspect, to make that very precise, what we mean by this discretization invariance is once I've trained my deep learning framework or a model, I should be able to query at any point in the domain, right? It's a continuous domain. So I should be able to go to that point and ask, what is the solution here? What is the output here? So that's one. But the other is also it should have some kind of consistency. If I now start with a certain resolution and continuously refine it, it should converge to a limit, right? So as you go to this infinite refinement, it should converge to what we call a continuous, right, limit, which would be the operator which maps between the two function spaces. And so that kind of like refinement means like you don't have vastly differing solutions at different resolutions. You shouldn't have that, right? You should kind of have a consistency in the model that should be built in. And then that makes those solutions much more trustworthy. And so that's an aspect that neural operators we show have. Of course, I haven't still told you what a neural operator is, but we show that they have the property of discretization invariance, whereas standard neural networks don't. And even if you add interpolation to standard neural networks, they can't approximate universally in function spaces, meaning you get a bad approximation error, as we said, because the neural network is trained at one finite resolution, and you try to interpolate to a higher resolution, you tend to get a bad error, and that's what is the lack of the guarantee of universal approximation. So given this, let's see now how neural operators are able to resolve the issues that we see with existing deep learning approaches. So the intuition comes from the simple class of partial differential equations, which are linear partial differential equations, right? So these are probably things you studied in a course. And what we know is that the solution of linear partial differential equations is an integral operator. So the inverse is integration. And we can write it down as integration with a kernel. And in many cases, like say, the diffusion equation, in this case, uniform diffusion, you even know what that kernel is, right? So this is something we are aware of, but we don't want to limit to just linear equations, right? We want to go to general nonlinear set of partial differential equations and other operators. And so in that case, how do we use this intuition? So the way we'll use this intuition is, let's say I design a block that computes an integral linear operator. So by itself, it's limiting because it only has a mapping that's linear. But on top of it, what if I add a nonlinear activation function? So this is what we do with standard neural networks. We have a linear function, like a matrix multiplication in a fully connected network, or convolution, which is also linear, right? But we add nonlinearity. And that's what makes it universal approximative, because nonlinear compositions allow it to now approximate any general function. And similarly, we use that intuition also with neural operator. We can incorporate a block that is solving for an integral linear operator. I haven't yet told you how we do that actual operation, but let's assume such a block exists. Now, on top of it, I want to add nonlinearity so that I can compose and get a universal approximator. So now the question is, how do I design this integral linear operator in an efficient way, right? And that also guarantees discretization invariance, meaning I am able to take inputs at any resolution, right? And I'm able to guarantee that if I keep refining my resolution, it converges to a limit. And hopefully that limit is the actual underlying mapping between function spaces I want to learn. And so the way we go about doing this is we, first of all, simplify it to asking, what if this computes convolution, right? And this kernel, can we now learn, or more importantly, can we just solve this convolution operation in an efficient manner? And so signal processing 101, what we know is convolution can be solved in the Fourier domain, right, in a change of basis. And then you can learn the coefficients in the Fourier domain and do inverse Fourier transform. So this is an efficient way to solve for convolution. And so that's the aspect we built. We now have this block by taking Fourier transform and learning coefficients in the Fourier domain. So we're asking how different frequencies, how they should be multiplied with different coefficients. We're learning those, and we're going to take inverse Fourier transform. And this by itself is linear, right? But on top of it, with nonlinearity, we have an expressive model. And we can show that this can universally approximate any mappings in function spaces. And that's the simplicity of it, because there's a lot of existing methods, numerical methods, that do solve in the spectral domain, right? We are using intuitions from that. But on the other hand, we are having nonlinearity. So that means it's not just limited to having only a low frequency part of the spectrum, right? Because if you only try to approximate in the Fourier domain with few coefficients, you cannot maybe span the whole spectrum. On the other hand, if we do nonlinear transformations, we can cover the spectrum even if there are many high frequency components. And so that's the benefit we get, the expressivity we get by adding nonlinearity to these spectral domain learning. And so that's the architecture. And as a brief comment, right? Convolutional neural networks also learn filters, right? They're solving for convolution. The difference is they're just local filters. They're just processing a small region. And they are learning at one resolution, one discretization. And so it doesn't easily transfer over to other discretizations. Whereas the Fourier transform, you can apply it at any resolution. And that's the benefit that we get by going to the Fourier domain. Or similarly, you can do other bases like wavelets and others, right? So that's the benefit of this. But the Fourier is a good use for many of the problems. And so as a simple showcase of this method, we can train at a coarse resolution data of this Navier-Stokes equations here. And we can directly evaluate it at higher resolution with no need to train again. So you've only trained once, and you've trained at a certain resolution, and then you can go to evaluating it higher resolution, and that's the benefit you get with these methods. You can also add physics into this. So far, it was purely data-driven, right? So on the other hand, if you want to also incorporate some of the domain constraints, for instance, if I'm solving partial differential equations, I know I want to satisfy the equation. So I can add that as a loss function. And I can then train this end-to-end. So you may have heard of physics-informed neural networks, which does try to solve for equations. But the difference there is it solves at one instance of a problem, as opposed to the neural operator, which solves over many instances to learn the operator for the entire family of partial differential equations, right? So you're getting both data as available as well as the equation. So you can combine data and physics together and get the best of both the worlds. And the other benefit is by doing it through the Fourier neural operator, you can solve for differentiation in the Fourier domain efficiently. That's a detail, but that also helps us. And the other way to think about this is also this operator learning, right, learns over many instances of equations. And now at test time, you want to solve one particular equation, say one kind of boundary condition, one kind of initial condition in your PDE family. And that requires further fine-tuning, and you can do that by enforcing the equation. And so this gives you the flexibility to further refine and get a lower error than was possible with just purely operator learning. And also, it helps you transfer across different physics, right? For instance, if you have like Navier-Stokes equations with Reynolds number 100, you train on this, and you try to test on Reynolds number 500, there is a distribution shift. So you don't expect it to work well directly. On the other hand, if you've incorporated the physics laws, the PDE laws, you can transfer it much more effectively because you know what changed in the physics between these two domains. So it helps with transfer learning, meta learning much more effectively than only a data-driven approach. So let me show you some examples of neural operators. So we use this to train a weather forecasting model, and you can see here what we call ForecastNet, the atmospheric rivers, which impact, right, moisture here in the western coast of United States a lot. You may have seen the atmospheric river storms earlier this year, where that had a big impact on the coastal regions. And so we can do such forecasts very effectively. But we can also do it much faster than numerical methods, about 45,000 times faster. And we can also predict all kinds of extreme weather events. So here there are contour plots that are showing high wind speeds, and in particular, this was Hurricane Matthew. That wasn't in our training data set, right? We are looking at inference, and we are seeing that it is able to accurately capture the trajectories of hurricanes. And we can look at the performance also on these extreme weather events, not just the normal weather events. And so the benefit of such a data-driven approach is we can use the wealth of historical weather data available, about tens of terabytes, and I think latest is even hundreds of terabytes of data available. Whereas numerical weather models barely use that historical data just to calibrate a few parameters, right? So that's the benefit you get with data-driven approach. You can learn from the wealth of data when it's available. And you get the speed up, and the benefit of that speed up is you can also do like larger ensemble members and better risk assessment. So this is something we are now exploring on how can we even do better than the current numerical weather models, because it's so expensive to do a large ensemble set for traditional methods. So we can also address questions like climate change mitigation. I mean, one of the approaches is to do carbon capture and storage, right? So once we get carbon dioxide deep underground, we need to pump that into a reservoir with water. And this, what we call a multi-phase flow interaction. How does water and carbon dioxide interact, and what kind of a pressure buildup will happen is important. And we are able to do this across multiple wells or multiple reservoirs. And this is an input to our model. So this says how permeable are the rocks, right? So if I know my subsurface and I've done exploration and I know the characteristics and I input this model, once I do this, I can now come up with simulations of the gas plume. So how does the carbon dioxide, as you're pumping it over several years or even decades, how does that gas plume change? Because you don't want leakage, right? You don't want a big pressure buildup. So how effectively can you store this is something really important. But we are able to speed that up about 700,000 times with our Fourier neural operator-based methods compared to numerical solvers. And also, there is the flexibility of being able to do very fine resolutions in the reservoir versus outside, right? I mean, you still remember these wells are connected because there's still some permeability. So you still need to simulate all of the area, but you can look at multi-grid approaches where you have coarser grids across wells and finer grids within the wells. And this kind of nested approach leads to even further acceleration. We can also handle different geometries. So far, I talked about uniform grid because fast Fourier transform works on uniform grid, right? But so many scientific domains don't have uniform grids. And so what we want to do is, in this case, if you still want to use FFT because fast Fourier transform because it's so fast, we want to learn a mapping between a mesh that is adaptive and non-uniform, and which is invertible mapping. So if we can deform, go back and forth, we can still learn in a latent space the fast Fourier transform-based coefficients, but go back to the physical domain. And that's what we did in this extension, where we now convert the physical domain, which can be a non-uniform grid, to a latent space that is uniform grid. And we do all the learning in this uniform grid in the latent space and come back to the physical domain and do the predictions on the actual physical shape at the very end. And so this leads to efficient learning as well as the ability to handle all kinds of different geometries. So this is the prediction. It's a plastic deformation. And you can see that you can have different kinds of impact on this, and it will predict how the deformation happens. And it can do that about 100,000 times faster than numerical methods. And not only that, once you have this ability, you can do inversion, right? Not just forward simulation. So you can ask now, instead of a given shape, what is the simulation? I can ask the reverse, give me a shape that optimizes certain design characteristics. And in case of airfoil, it is drag versus lift, right? You want to minimize that. You want good lift, and you don't want drag. And so you can ask, in this simple airfoil shape, how do I directly optimize for that? And so the benefit of a neural operator approach is it's differentiable. So you can directly search in the design space and optimize for that and get to very effective designs fast. And we are also working on this with catheters, and where the idea is you want to prevent bacterial contamination. You don't want to prevent bacterial flow. And we can, again, optimize for the design because you don't want the bacteria to come here. So you can ask, if there's a lot of bacteria here and it's flowing upstream, you don't want it to come inside your body, right? So, and that's something we can do. And these are things we are testing in the lab and showing that you can reduce bacterial contamination by about 2 orders of magnitude using this method, and directly doing inverse design by asking what kind of shape of grooves do I design, how they should be spaced, what angle it should be. So I can directly do these design objectives, and do it very fast because we have now the fluid simulation being much faster than possible with CFD solvers. So far, I talked about predicting trajectories, right? How does the fluid flow or how does the plastic deform? You can do that in short time scales. But in many of these systems, if you run it long enough, it will be chaotic, meaning even small perturbations can lead it to very different answers in the end. And that's true with especially climate simulations, right? So you have like certain initial conditions, and if you run it long enough, it's hopeless to try and predict what the trajectory is. And so the goal should be different, not to predict the actual trajectory over, say, the next decades of what climate will be, but the statistics of it, right? So, and so there's a notion in many of these systems known as attractor. Even though the trajectories diverge, you can now specify what the invariant measure is. You can characterize it. And so can we learn those characteristics in our neural operator model, even if we cannot hope to predict the trajectory over a long time period? And this is something we do by enforcing dissipativity, which is the fact that you do not want your model to blow up, right? So because if small changes build up, small errors build up, and then they become diverging, that is a problem. And so we do that by enforcing a certain dissipativity. And with that kind of dissipative regularization, we can see that we can keep the system within, right? We can try to approximate the attractor. It doesn't diverge, whereas standard approaches without it will diverge. And so with this, we can simulate a chaotic system effectively without leading to blow-ups. And we can capture the invariant statistics, different kind of statistics of the attractor effectively. So and this is, these kind of approaches have such a wide range of applications. I want to briefly talk about how we can use this to build autonomous systems. So here at Caltech, we have the CAST, or the Center for Autonomous Systems and Technology. I think for those who are visiting students, you will get a tour of it during your visit, right? So, given all the expertise there and the challenging requirements for autonomy, what can we do with the use of neural operators and other machine learning approaches? So one aspect we are exploring is how we can do effective flow-based control. And this is true in the biological realm. If you think about fish or birds, they're so agile and they can detect minute changes in flow very effectively and adapt to it. But our drones, our aircrafts are far from that, right? So there is still a huge space of being able to handle extremely turbulent wind conditions. And so this, we are testing it in the lab and asking, what can neural operators learn and how effectively can we do real-time flow prediction? Because ultimately, we can then build it into drones and other autonomous systems and handle whether it's air or water flow effectively in turbulent conditions. And you can see that we can control the error, because the other good thing about these systems is you're getting feedback, right? So you have to track for the error. So you want to predict it for the next, say, few seconds, and you get further feedback from the sensors, and you want to be able to ensure that you don't crash. If it's a drone, you're still up in the air, you're able to stabilize. And so there are different considerations, but using neural operators within that approach can be very effective. And this is something we're exploring with Mori Garib's group. And as well as adding in reinforcement learning and other approaches. So especially because it's not just learning offline, can you also adapt online effectively? And there are efficient approaches that are also Fourier-based, which we show model-based reinforcement learning that can stabilize with much less training samples than other approaches. And the other benefit is we have like the wind array, the fan array for simulating all kinds of wind conditions, and we can test our drones. And so this also gives us the ability, it's not just simulations, we can take that to the real world. You also saw that with the catheter example, right? So simulations are great, but we need to ultimately anchor it in the real world, and that's why working with experimentalists to get that all the way, into a 3D printer or into the real drone is very exciting and interesting. So I want to just show a few more just examples of what AI can do in chemistry and biology. We have an extensive set of collaborations going on, but I'll just show you one example, which is what we did for understanding how the coronavirus interacts with the respiratory aerosol, right? So with the droplets and how does it interact inside our lungs. And so this is very important to understand the impact of coronavirus as well as how does it transmit, how infectious it is. And so we did a combination of traditional simulations along with the use of AI-based methods, including neural operators as well as other AI-based methods. And so what we wanted to ask is these, what you see in yellow here are calcium ions. So how well do they bind to the spike protein in the coronavirus? And understanding this amount of binding will tell us how does it leave in this respiratory aerosol, right? How transmissive it is. And so being able to do these simulations is very important. And what we did here was to be able to build surrogates for quantum chemistry and do that over thousands of atoms, which would not have been possible with traditional methods. And so again, AI can help you come up with now unprecedented simulations and insights that would not have been possible otherwise. Yeah, so to conclude, I do think it's an exciting time to work at the intersection of AI and scientific domains here. And at Caltech, there is such a vast set of domain experts who are very much willing and excited to work with us in enabling this. But that also means closely understanding the requirements, right? So many times just plug and play doesn't work. Using standard AI methods means most of the time it's only going to work within that training data domain. It does not extrapolate. And that's been an ongoing theme I see again and again, right? So if you're happy with a limited performance of an AI method within the training domain, that's great, right? There are standard tools. But most of the time, that's not the case. You want to make new discoveries, right? So meaning new discoveries means you don't have it in the training domain. There's going to be a distributional shift. You want to do climate simulations. We don't know the climate 100 years from now. We want to come up with estimates of it, right? Good confidence bounds, but we don't have it. So we don't have the training data to train for it. And that's what makes it a lot harder. But that's where I think combining the domain requirements, domain constraints with data-driven approaches can really lead us to the future. And neural operators, I think, are an exciting realm there because instead of asking to learn at one specific resolution or discretization, it allows us to directly learn in function spaces. And so that's one aspect we can remove, worrying about how limiting to one discretization may affect your simulations, right? So we can bring in different resolutions of data. We can bring in physics at a higher resolution than the data we have available. And with that combination, we can get very high fidelity surrogates for many of these simulations. Thank you.
Thank you, Anima. I'd like to open the session for questions. In asking questions, I ask that you come forward and use the microphone. And I'm going to give you time to pluck up the courage and get up, stand up, walk down, and ask a question. But this whole event will be much better if you do ask questions, and I'm sure many of you have them. So let's have somebody come up and ask a question. Thanks.
Yeah, so for, I guess, the Fourier operator, do you have any estimate of size? Like what's the size for that training, since it seems to rely on the training set necessarily to kind of do the extrapolation, if that's an incorrect word?
Yeah, that's a great question. Of course, right, the short answer is it depends on the domain. But what we've seen is very efficient learning in terms of the number of parameters needed. So if you recall, the parameters are learning the Fourier coefficients. We do also add a regularization where you only retain a few low-frequency modes in each of those layers. So you don't learn coefficients across all frequencies, and that's also good regularization. And that also makes it compact. And in fact, one of the recent works, Robert is here, we've been doing is to even learn incrementally. So you don't have to learn all the full spectrum right in the beginning, right? You can start by progressively adding more and more frequency modes across multiple layers of nonlinearity. And with that, you can also save on training costs, but also get better generalization.
Thank you for the talk, Professor. I'm curious, like a lot of times with differentiable simulation, one of the concerns is the quality of the gradients that you get for inverse tasks. What has your experience been with sort of traditional differential simulators and sort of how noisy those gradients are versus neural operators versus maybe other neural network-based approaches for things like fluid prediction, which are like graph-centric?
Yeah, so I mean, it certainly, again, depends on the domain, right? So if you're asking about, say, inverse design, so it depends on like that design space, right? How differentiable it is, and how noisy are the gradients. I mean, the benefit of this is, right, you can start with a candidate of design, but you can further refine it, right? You can use other tools. But in our experience, we didn't see that as, at least in those domains, as a big factor.
Thank you so much.
Hi, Professor. Thank you for the talk. My question was on the non-uniform grids, the FFT. I think that's a very cool topic where you go into the latent space. But I was actually curious to know, did you use any, I think the fast Fourier transform like HALE is one of the greatest algorithms, right? And there's been approaches on quasi-linear, I think, algorithms for non-uniform grid sizes. Did you ever try them to do it directly instead of embedding into this latent space, or just the direct convolution comparison?
Yeah, no, that's a great question. There are certainly non-uniform FFTs, right? But it's again one of practicality. The code isn't really out there, right? I don't think there's a CUDA implementation for GPUs. So that's one. And the other is, from what I understand, the computational speeds can greatly vary. And whereas in this case, it's still the same computational cost across different grids. Okay, and in a way, the intuition is, again, by learning to deform, you're learning kind of more features about the geometry better, right? So that could also be a nice approach to, because we do know adaptive meshes have this notion of deformation, right? So that was another intuition we thought would be useful here.
Makes sense. Thank you, Professor.
Yeah.
Hi, Anima. You had a slide comparing FNO with DeepNet and interpolation. Can you unpack what you meant by interpolation?
So yeah, sorry. Interpolation is take any standard neural network trained at a fixed discretization, and then on top of it, you do an interpolation like bilinear or any of the standard interpolation.
Got it. Thank you.
So there's no learning in the interpolation, right? So there's only learning of a neural network of a fixed size. I mean, you could also do learning-based interpolation, but the idea is you're only starting with a neural network that's trained on a fixed resolution.
Got it. Thank you.
Yeah.
Hi. Thanks for the talk. I also had a question on the adaptive grids and going back and forth between the adaptive grid and latent space. Are there conditions where that works well, or have you found that you can go back and forth pretty much with any adaptive grid that you've seen?
Yeah, no, this is a great question. So it depends on the topology, right? So, I mean, yes, if it is diffeomorphic with respect to a torus or, in, say, our sphere in higher dimensions, right? You can do this transformation. And if it's not, then there is something known as domain decomposition. You can cut it up and then arrange it in a way to make it diffeomorphic. So from topology, we do know, like the short answer is we do know cases where it directly works, or you need to do domain decomposition and further ways to make it work.
Thanks.
Yeah.
And does that work? Does the domain decomposition basically cover all of the cases?
Yes, yes.
Thank you.
Yeah.
Hi, Professor. Really enjoyed your talk.
Yeah.
I had a question about kind of the computational cost of training something like ForecastNet, and it seems like at inference time it's much cheaper, and kind of that training cost gets amortized if you do a lot of inference with the model. So maybe the question is like, how much is it to do the training, and like, and how is that relative to doing a traditional simulation just for one scenario?
Yeah. Yeah, I mean, it wasn't even that expensive to train. At least the first cut of the models we did was like, say, over less than 2 days, right, on 64 GPUs, if I recall. But something on that order. So it's not like a language model scale training, right? Although you can ask, okay, I could make a bigger model and I could make it much more effective. So I do think the training costs are very manageable compared especially to like language and other models we see. And the other thing is, as you said, right, it's amortized. Numerical simulations, if you're doing weather, you have to do it, right, every day and multiple times a day. And so this you train once and you run it. And when it's inference time, it's a matter of quarter of a second compared to hours to get on a big CPU cluster for traditional simulations.
And for something like FNO, what are the dimensions that you can scale up the FNO model, for example, and what sort of, do you expect significant performance improvements if you do scale up the FNO model? What does the power law look like, basically, for
No, that's
FNO?
a great question. And so, the many hyperparameters, right? One is the number of layers, of course, what is the depth? And the width here is how many frequency modes do you retain? Because as I said, as a regularization, and also to get better generalization, which is the reason of regularization, right? We are only keeping few frequency modes. And so that's a hyperparameter, and that's what in the recent work that Robert was part of, where we can incrementally grow this, which makes it even nicer. You don't have to tune that hyperparameter beforehand. It's something you learn as you go. So compared to traditional networks, that's the other nice thing. There aren't a lot of parameters to tune for.
And in terms of performance improvement, it sounds like it would mainly be expressivity and also just finer grained predictions.
Yeah, exactly. Because the more frequency modes you keep and more layers you have, the more high frequency components you can capture, right? But it's also a trade-off because you don't want spurious high frequency components and lack of generalization. And that's what doing it incrementally helps you lead to better regularization and generalization.
Right. Thank you very much.
Yeah, thank you for the talk. I have a question about errors, like if you measure data and they're really noisy, and from experiments, how robust all the operators are towards this error. Is it still predicting quite well the underlying operators, or how the errors influence it?
Yeah, no, that's a great question. So we are doing that very methodically now in the weather domain, right? Because there, what matters are these ensemble forecasts. So we want to ask now, if we do there is different sources of uncertainty. There's uncertainty in the initial conditions, right? As you said, if I perturb, what will the output be? And there's also the model uncertainty we can ask, can we also incorporate it? And overall, are we going to match the uncertainty of the gold standard, right? The current numerical weather models along with their ensembles. And we show that we are able to do that. We are able to get probabilistic forecasts as well. And so we do some calibration on top to make that happen, especially how to calibrate the initial conditions. But with that, we are able to get the relevant spread and the right statistics.
Okay, thank you.
Hi, thank you for the talk, Professor. So I had a quick question about scalability. I know there was a question about gradient stability and that kind of thing, and you mentioned there's some, maybe depends on the domain. But I'm curious what you think about the feasibility of using techniques sort of analogous to, let's say, traditional CNNs, like batch norm, residual skip layers, that kind of thing, to sort of like further extend these models or scale the models and make them deeper, and whether that's been tried, if you think it's possible.
Yeah, no, that's a great point. And these are all aspects we've investigated, right, and built into the libraries. And so, yeah, different forms of normalization help. I think batch norm to a less extent here. There are other normalizations that are better. And skip connections also help, especially for the aperiodic signals, because learning it through the Fourier domain, you can't do that with Fourier continuation. So that's something we are also now incorporated, right? But the skip connections could make it easier. So yeah, so these are all different architectural aspects that we discuss in the papers, build it into the libraries. But yeah, I agree. Bringing in all that knowledge, what we've seen in other neural networks, right? Certainly. So that's something we're continuously doing.
Great, thanks.
Yeah.
One other quick question, if it's all right. So you mentioned, with the physics-informed neural networks, how you guys can build sort of domain-specific invariance into the loss function. But is there an idea of sort of building implicit biases into the architecture? Say again, like the way CNNs sort of have implicit bias in the sense of shift invariance or scale invariance. Is that possible with these FNOs?
Yeah, so first of all, the Fourier transform is a nice inductive bias, right? And that's what we see with all the pseudospectral solvers in traditional methods as well. They exploit it, and they work well for certain domains. And so that's a nice inductive bias that's already built in. And if you're asking for specific things like equivariance, right, that's a further question, because now all those operations should be equivariant. And this is something we are investigating. And in fact, for the weather domain and other problems on the sphere, we are now looking at spherical harmonics instead of direct. The fast Fourier transform is on the Euclidean domain. And that also improves a lot, right? Especially not just predicting weather short term, but asking for long rollouts and looking at stability there. So to me, inductive bias is great for extrapolation, because you can expect better stability, more graceful degradation compared to the models that don't have it.
Thank you.
Yeah. Okay, thanks. I think one last question, Frederick.
Can you maybe talk to the adoption in scientific applications, maybe compared to FMs, for example, with regards to theoretical guarantees? Because it seems to be a newer field, so I don't know how reliable these methods are. And can you maybe talk about the process with regards to showing how well they converge with the amount of data, and how the process is in that area right now?
Sorry, were you saying comparing to neural fields?
I don't know, for example, comparing to FEMS or something in a PDE application, if you compare it to I guess the classic methods.
Yeah. So are you talking about how fast do they converge compared to FEM or other methods, right?
Yeah, I mean, maybe generally theoretical results for PDEs.
Yeah, so I mean, the theoretical results for FNOs and others are mostly so far in the approximation domain, right? We can show that there exists an architecture that can approximate, and to what extent, especially for families, say Navier-Stokes, you can come up with those approximation bounds. But when you're asking about convergence, that's optimization in a nonlinear realm, right? So, so far, those results don't exist, but I wouldn't rule it out. I mean, that's an open question. If we can theoretically also prove how well can you train these models and what do they converge to.
Okay, so you can show that you can approximate it with your architecture, but it's not clear yet if your algorithm, the optimization converges to the. Okay, thank you.
Yeah. I mean, that's true for a lot of the deep learning too, right? Like kind of how well can you train is, in some limited settings, people have optimization guarantees, but in most other cases, such guarantees are hard. But I wouldn't rule it out. That's an open question.
Okay,
yeah.
Thanks.
Yeah.
Okay, let's thank Anima for a great talk.
Thank you.
And also, thank you all for asking lots of questions. Let's keep that going all day. Makes it for a better event.
Are you using the mic or?
I will. I'll use it.
Are you going to take a break or just continue?
No, we'll keep on time. Yeah. Know where to put this.
Yeah, there you go.
Yeah, thanks for all the questions. So keep that coming and continuing the theme of how to effectively do surrogate modeling and supervised learning in scientific domains, and now specific to these continuum mechanics. Andrew Stuart will be giving the next talk.
Thanks, Anima. So I'm going to carry on the theme that Anima introduced of using ideas from deep learning, supervised learning, to study problems arising in partial differential equations. And in particular, I'm going to concentrate on a number of research directions related to various applications in continuum mechanics, and in particular collaborations between the research activities in the CMS department and other more applied parts of Caltech. So the work is joint with many people, and I just want to highlight in particular Tapio, who will be talking this afternoon in relation to the climate modeling work I will discuss. Kaushik, who will also be speaking this afternoon in relation to the homogenization and material science work that I'll describe. And I also want to point out current PhD students at Caltech, Akila and Margaret, both working in these areas. And Anima, who's just spoken, and Zhongyi, who's played a major part in actually making these methods practical. As you saw from many of the questions, there is a lot of tuning to be done to make these methods effective, and tuning in a scientifically principled way in the context of really interesting applications is something that Zhongyi has had a lot of input to the research on, and that has affected a lot of our understanding as to how these neural operators work. So my talk is structured this way. I'll talk about supervised learning, which is, of course, was underneath everything that Anima said in the previous talk. I'll describe a mathematical framework in which I will be working, and I'll describe a number of different architectures, starting with simple GPs, going up through some more complicated and leading to the Fourier neural operator. And then I'll talk about 3 classes of problems arising in applications in continuum mechanics where the use of neural operators has the potential to impact science. So the first is learning the parameter to data map, and that's something you've already seen something of in Anima's talk. I'll go into more detail. The second one is the learning of constitutive models. I'll be doing this in the context of material science problems, but the ideas are more general. And then this idea itself falls within the topic of homogenization and learning what I'll call the homogenization operator. So I'll say a little bit about that at the end. This talk is a little bit more technical than the previous talk, and you are a heterogeneous audience. Please do stop me and ask me questions if things are not clear. Okay? And you don't have to come up and use the microphone during the talk. I would like you to do that after the talk. If you have a question during the talk, just raise your hand and ask me, and I'll repeat it so that it's recorded and so everyone can hear it. But do ask questions. Okay, so the setup I'm going to work in is everything I will describe will be related to supervised learning. And what will differ between the different examples is the choice of the input space and the output space where the data pairs live. So throughout this talk, the input and output spaces will be calligraphic E and calligraphic S. We'll be trying to learn about a supposed true input-output map, psi dagger, which maps from the input space E to the output space S. And we'll be given data in the form of pairs, En and Sn, where the Ens are drawn from some probability measure mu, IID, and the probability measure mu lives on this space E. And the Sns that go with the Ens are assumed to be either equal to the image of En under psi dagger or approximately the image of En under psi dagger. And the goal of supervised learning is, given this data set, is to find a function approximator which is close to psi dagger from within a class of functions psi which map the input space calligraphic E into the output space calligraphic S and are parameterized by a finite number P of parameters. Right, so that's our objective, is to locate a parameter value theta star where this function a function from this class with a particular choice of theta is close to psi dagger. And for me, everything here, E and S will always be vector spaces, though of course many of the real early successes of supervised learning, S was not a vector space, but rather was for classification. But everything I do, these will be vector spaces. Okay, so what I'm going to do is describe a few architectures, that is, parameterized classes of functions psi that are relevant to the specific applications to continuum mechanics that I'm going to tell you about. And the first ones are Gaussian processes, and this is a topic that Houman will go into in a lot more depth in the third talk this morning. But the basic architecture here is that we seek a function psi, which is a function of input E parameterized by theta, which is simply a linear combination of kernels. And the parameters to be optimized appear in a linear fashion. And if you write down a standard L2 loss function, you get a quadratic optimization problem to determine the thetas, and it just leads to linear algebra to determine them. So none of the issues that we encountered in the last question about optimization. Finding the thetas here is relatively trivial. Nonetheless, this is a very powerful methodology, and the power really stems from two things: the ability to make this method work by choice of the design points, the EJs, and by choice of the hyperparameters gamma. And these are often done in conjunction with knowledge about the data. And that leads to kernel functions, which are the basis in which we make our approximation, which are data adapted and can be seen as a step towards neural networks. And although I've just written this down as a finite dimensional approximation in the span of these functions k, this can be derived from a perspective of optimization in function space. So these can be formulated that way. I'm describing them with E and S being finite dimensional Euclidean spaces, but they also generalize beyond that setting. And the representative theorem is used to determine the particular form that you see here. So there's a very rich structure and possibility of generalization for this methodology. Houman will talk about some of that, but I'm going to use the methodology in this form for a simple example in climate modeling in a few moments. Okay, so in that case, E and S were just finite dimensional Euclidean spaces, but I now want to make the step to the setting in which the previous talk of Anima was set, in which E and S are Banach spaces of time, in this case, time-dependent functions. In general, we will discuss Banach spaces of functions. And I'm going to introduce something that we've called the recurrent neural operator. This has a very simple form, and although it is an operator which maps Banach spaces of functions into themselves, E and S are both Banach spaces of time-dependent functions in this context, what needs to be learned are two pairs of fixed neural networks between finite dimensional Euclidean spaces. So let me show you the structure of this architecture, and then later in the talk I'll show you how we use this in problems in material science. So the goal here is to map a function E of t into this function, psi RNO, for recurrent neural operator, also a function of time. So psi RNO takes as input a function E. It has some parameters which we'll choose judiciously, and then that creates a new function of time. And it does that by applying a function that acts on a Euclidean space at each point in time to the function E of t, its time derivative, and an auxiliary variable r. And this function f is parameterized by theta. And the auxiliary variable r satisfies a differential equation which couples it back to the input E. So R solves this differential equation with the right-hand side G depending on R and E. And in words, this equation is an equation for summarizing the history of E. So this function up here just evaluates, f is evaluated at E at a fixed time t and a fixed time derivative of E at a fixed time t. Whereas the variable R includes historical information about the entire past of E through the solution of this differential equation. And I will show you that the mapping that results from this architecture, which maps a function E of t to a function psi RNO of t, is very useful for a wide class of problems arising in continuum mechanics. So this is kind of in between the previous example that I described, which was on Euclidean spaces, and the next example that I will describe, which is the Fourier neural operator that you've seen already in Anima's talk. It's in between them because it maps Banach spaces of time-dependent functions into one another, but all that needs to be learned is a pair of neural networks which act between fixed finite-dimensional Euclidean spaces, the functions f and g. And the examples you'll see in this talk, f and g, are just four-layer neural networks with the last linear layer. And in fact, there's no real reason, there's nothing special about using neural networks here. You could use GPs for f and g, and this method would work just as well. The key point about this architecture is how it captures the history of E through the latent variable R and uses that in this form that I've written up here through the function f. Okay, so we'll return to this in the context of material science in a short while. And then I wanted to discuss the Fourier neural operator. I'll just do this briefly because Anima has already described it. But it is made, as you saw in Anima's talk, by combining an integral operator with an affine transformation which acts pointwise on the function v. And then the application of a nonlinearity, an activation function, again applied pointwise on the function that occurs inside these large brackets. And that gives the definition of Lj applied to V, and we recurse on that. And both at the beginning and at the end, we apply a pointwise neural network to the function E, which is the input. And then the output of this is a function psi fno, which takes E as input, is parameterized by a bunch of parameters I'll highlight in a second, and gives another function of variable z in some domain D. So as described here, this is a mapping that takes E and S are both Banach spaces of real-valued functions on a domain D in RD. And the parameters here, the parameters of the initial and final neural networks, which act pointwise, these affine transformations, which act pointwise, and this integral kernel, in which we compute using convolution, and the learning of the parameters theta prime that describe the Fourier transform of the kernel of the integral operator. So as Anima showed, this is a very effective architecture for many, many problems. I will very briefly touch on a final architecture, which I call PCA-net, but it's such a small part of the talk that I won't labor this slide. What I would like to say is that if you're interested in following up on any of the references in this talk, I'm happy to make the slides available to you, and there's an extensive bibliography within them. So please just email me if that is something you would like. Okay, so I want to return to a question that was raised in the questions after Anima's talk about efficiency of these methods and comparison with traditional PDE solvers. Because I think that is a key question in this area, whether or not we can firstly compete in terms of efficiency with existing methods. There's empirical evidence that we can. And secondly, whether we can back up what we do with theory that justifies the use of the numerical methods, the use of numerical methods based on neural operators. So firstly, let me say that two leaders in this work are Nick Kavatsky, who is a PhD student here and now works in Anima's group at NVIDIA, and Sam Lanthaler, who did his PhD at ETH and is now a postdoc here. And their work together has really founded has created the foundations of the theory of approximation theory for neural operators. And there are a number of results, and they take this rough form here. So this is a loosely stated theorem, but the type of theorems that we have relating psi dagger, the truth that underlies the data, to psi, which is with a chosen parameter theta would approximate psi dagger. The basic universal approximation theorems are the existence of choices of parameters which achieve an epsilon error. And this is achieved for two kind of results. The first ones look at the supremum of E over a compact set and assert the existence of a parameter theta for which it is possible to approximate psi dagger to error epsilon. And the others involve averaging over some probability measure on the whole space, and then again obtaining an error of size epsilon. Neither of these types of results go to the question of efficiency and the question of how these methods compare with, say, with finite element methods. That question, which relates to the question of cursive dimensionality, is something we're starting to understand, again, very much through work of Sam Lanthaler and Nick Kavatsky. The cursive dimension addresses the question of not just can we approximate, but how much does it cost us to get an error of size epsilon. So this is something which is an area which is really in its infancy, but I think to make this methodology useful in science and engineering, we need a lot more analysis in this area so we can justify the methods that we use, really know what it is that we're computing, how much they cost to compute, and verify our computations, as well as assert that in some regimes we're more efficient than other methods. So this area, cursive dimensionality, is one that I think we'll see rapid growth in, but the problems in approximation theory are hard. In terms of universal approximation, there are universal approximation results for everything I'll talk about today, and also for another class of methods that I won't discuss, but which is also very useful in this area, the deep O-net methods that come from the Carniadakis group at Brown. Okay, so that said about the general setting in which I'm working, let me now talk about applications of those architectures and what we've done with them. So the first I'm going to talk about learning the parameter to data map. And I'll explain what I mean by that. There'll be two classes of problems. The first one is motivated by work with Tapio Schneider that he will talk about in more detail this afternoon in climate modeling. And this figure summarizes the basic idea. There are problems that we're interested in climate modeling where we wish to calibrate a small number of parameters that describe important parts of the model. And in particular, in relation to Anima's discussion earlier about modeling of clouds, these are parameters which describe processes that are a surrogate for fully resolving clouds, which is currently computationally impossible. So there are a small number of parameters that characterize this part of the model. They get run through a very large PDE model to map to the space where data is acquired, for example, through satellite measurements. So in this problem, what we're interested in is to use satellite data, for example, to learn about a small number of input parameters, and yet to compute the parameter to data map, which needs to be done repeatedly during a calibration process, especially if you're doing uncertainty quantification alongside. One has to, at each step, solve an expensive PDE model with millions of variables. A useful concept, and this is not new to machine learning, this is something, surrogate modeling, that has been widely used throughout computational science and engineering. A useful concept is to replace this black box in the middle by something simpler, and we're going to use a Gaussian process, which is much faster to evaluate, and then use this computational layer as a surrogate for this more expensive one. And we've done that very effectively in the context of climate modeling. So let me just give you a taste of what is involved in there. So the PDE model that I referred to involves a set of partial differential equations discretized on the sphere and in the vertical, so in 3 spatial dimensions. 2 of the equations written here for moisture conservation and energy conservation, so temperature and the amount of moisture in the air. And these are coupled to further conservation equations for mass and momentum. These equations have in them some unknown parameters, which I call E. And in the example I'll show you, there are just 2 of them. And the data that we're using to try and learn about these parameters is of size 100, roughly. And it's made of 30-day time averages of relative humidity, precipitation rate, and the frequency of extreme precipitation. Now, this averaging is important here. So because we're talking about climate, it's statistical data that's really relevant and that we want to match to. But this data is noisy because it's not averaged over an incredibly long time. And to give you an idea of that, I'm plotting here the loss functions. These are not the loss functions for training. These are the loss functions for parameter calibration in the physical model. They're very, very noisy indeed. However, by using GP, which is shown here, the mean in dark orange with a couple of standard deviations lightly shaded in orange, in light orange, we find the smooth envelope from this data, and we're able to solve a simpler, smooth optimization problem. And we're also able to do uncertainty quantification, which also uses these loss functions in a very efficient way. So by using GPs, not only did we speed up the computation, but we also are able to remove noise that is inherent in the way the data is acquired through time averaging. You can think of the orange smooth curve as an infinite time average, which is what we would really like to work with, and which we recover by the use of this GP methodology. Another point is that the design points for the Gaussian process is crucial, and we use a methodology based on ensemble Kalman inversion to do that and make this successful. Okay, so that's one example, and that shows the use of GPs. I now want to show the use of FNO, and this example was in Anima's talk. So here, the use of the neural operator, rather than a GP, is to sidestep PDE time stepping. So the inputs and the outputs here are functions, the parameters and the data in the general terminology I'm using in this section. So the input parameter is the initial condition for a fluid flow, and the output parameter is the solution of the fluid flow at time t. This might be the velocity field or vorticity or stream function, something which characterizes the fluid motion. And in between these is a PD model that must be time-stepped, so integrated over small time increments to go from time 0 to time t. We can, however, replace this by a Fourier neural operator and evaluate this mapping much faster and yet preserve accuracy. So the equation, the specific computations we've done are in 2 spatial dimensions, which enables the use of a vorticity stream function formulation of the Navier-Stokes equations. And we have learned the mapping from the initial condition psi 0 to the solution at time 1. And there are relevant function spaces here we can go into, but the key point is they're spaces of periodic functions. And this is exactly the example that you saw some simulations for in the previous talk. So this, again, the fact that this computational surrogate is much cheaper than solving the PDE by traditional methods enables the solution of, for example, inverse problems, where one tries to determine the initial vorticity from measurements made at later times. If you solve those problems with uncertainty quantification, you end up solving the forward problem that's integrating this way many hundreds of thousands of times, and replacing the PDE, traditional PDE solver by a neural operator enables those evaluations to be performed much more quickly than they can be performed with the standard integrator. Right, so both of those were examples where we replace something expensive with something cheap, and that enables us to move into realms of computational science of engineering that were not accessible previously. However, as I've said, if this really is to make an impact on science and engineering, I do want to highlight that there is a need for theory. Computational science and engineering based on, for example, the finite element method has been enormously successful, not only because it's efficient and a widely usable methodology, but because it comes with a theory that guarantees in fairly prescribed settings, but nonetheless guarantees in certain settings that you compute something with a certain level of accuracy and a certain cost. And we're simply not at that stage in this field of scientific machine learning. And if it is to impact science and engineering, we need to get to that point. So there are many, many open questions in this area. We're at the beginning of the field, and that, of course, is a great thing for you guys. Especially the younger you are, the more great it is. I'm going to talk about a different application of learning neural operators, which is to learning of constitutive models. And this is going to take us into a specific class of partial differential equations that arise in continuum mechanics. And I'll spend a little time telling you about those equations, make a link to homogenization, and then finish with some observations about homogenization in general. But in this part of the talk, initially, I'm going to link to the recurrent neural operator that I described at the beginning, and you will see why. So let me try and set this up. This is all about F equals ma. So the great thing about Newton compared with machine learning is that you could extrapolate Newton, and we can't yet really extrapolate machine learning as much as we'd like to, okay? Newton was highly extrapolatable, and that's a great thing about everything he did. There were imperfections in what he did, the perihelion of Mercury, and then by observing that, we learned more. And specifically, we learned more about special and general relativity. Being able to extrapolate is extremely important, and a motivation for the work that I'm describing here, in which we learn constitutive models. And embed the use of neural operators in the learning of constitutive models is that what we're doing is still embedded in the concept of conservation laws. So in the models that will arise here, we still have the notion of conservation, and we're still based in physics. So I want to take the time to explain to you how that works, having motivated that I believe it's important that we think about the use of neural operator in this way, rather than just replacing the whole model by neural operator, which is what I was doing in the previous examples. Here we're trying to embed a combination of learning and physical principles. So I'm going to talk about F equals ma, and the specific focus is going to be on F equals ma for describing materials and solid materials, so solid mechanics. And in many problems in material science, there are very small scale features of the materials which are incredibly important in the design of materials with desirable properties. So those small scale features are going to be captured in this F equals ma through the presence of something, x here is spatial variation, through the presence of a variable x over epsilon, where epsilon is a small number. And this represents variation in the physical medium at a very small scale. Okay, so bear that in mind. And then now I'm just going to write down F equals ma, or rather ma equals F. So on the left-hand side is mass times acceleration. And on the right-hand side are forces experienced by the body. And u, or u epsilon, is the displacement of the material at position x in space and time t. Sigma epsilon is called the stress, so that describes, it's a way of describing the internal forces in the material through the divergence of the stress. And F is a body force that you apply to this material. So you don't need to understand partial differential equations in depth to understand what I'm going to tell you in this talk. I would just like you to understand that this is ma equals F. And what characterizes different materials is the relationship between the stress, sigma epsilon, and the displacement, u epsilon. And for the problems we're going to look at here, that relationship is known through years of physical modeling that goes back centuries to be well described by a relationship of the form where the stress can be written as a function psi epsilon of the gradient of the displacement, which I'll refer to as the strain in this talk. And the curly brackets here mean that this may involve the historical dependence of this variable, so not just at the current time, but into the past. And finally, I want to highlight that because many materials vary at very small scales, this relationship between the strain and the stress will typically depend on something which rapidly varies with respect to the variable x, because epsilon is small. Now that rapid variation renders computation of this model beyond realistic timescales for predictions, for useful predictions. So a major goal in this area is to find effective models that remove this small scale. And that theory goes by the name of homogenization. And the basic idea here is to look for an approximation of u epsilon as a power series in functions u0, u1, u2, ordered by this small parameter epsilon. So u0 plus epsilon u1 plus epsilon squared u2. And there's a methodology for substituting this into this equation and deriving an equation for u0, which removes the dependence on the small scale and nonetheless recovers an accurate approximation of the solution of this equation. So that's the theory of homogenization. It leads again to ma equals F, but now the small scale dependence is removed. Now, there are many problems where it's known analytically how to do this, but for the most part, this is not well understood analytically. So characterization of the function psi, which maps information about the strain into the stress, is typically hard to characterize through a formula. And so I'm going to describe to you a methodology to learn about that function psi, which is an operator, by using data. So in the next few slides, you're going to see examples where the input space, calligraphic E, is made up of time histories of the strain, the gradient of u0, And the output space S is made up of time histories of the stress, sigma. And on that basis, we'll try and approximate the true homogenized operator psi within some class of neural operators. Okay, so just again, there's a lot of details in this slide that, depending on your background, you may or may not be comfortable with. But there is a take-home idea which is independent of the details, and that is that we're looking to embed conservation laws in the form of believing that Newton was right, and F equals ma, and combining them with learning on a very specific, well-specified subproblem, which is needed to complete the overall balance laws and give you a predictive model. So if we achieve this, we still have conservation of linear momentum in the form of equations of this form, and we focus our learning on the relationship between the strain and the stress. So let me first describe an example which comes from viscoelasticity. And we chose this example to start our study because this is one that's completely understood analytically and enables us to benchmark the methodology. Having done this, I'll show you the use of the same methodology on examples where we do not have a complete theory to justify what's happening. So this model has the following form. You have the divergence of the stress is equal to the body force. If you like, there's no inertial term here, so this is just a balance of forces. And in this specific model of viscoelasticity, the stress is related to the strain and rate of strain, as you see here, by a linear combination of the strain and the time derivative of the strain, where the linear combination is formed through functions that vary in space, nu epsilon and e epsilon. So e epsilon is given by of x is given by a universal function evaluated at x over epsilon, meaning this e epsilon changes very quickly, and likewise nu epsilon. And the objective of homogenization is to remove this small scale and find an effective equation valid in which epsilon does not appear, but yet which approximates the solution of this equation. I've not written boundary and initial conditions, but if you care about that and you get the slides from me, you'll see them at the end of the talk. Okay, so we know a lot about this theoretically, and I'm going to use this to motivate the recurrent neural operator. If the functions that characterize the material, that is E and nu, which are evaluated at x over epsilon and so rapidly vary, if they're piecewise constant, then it's possible to eliminate epsilon at the price of introducing memory. And here, by doing this, I'm making a connection to the recurrent neural operator. So by removing epsilon and performing this homogenization procedure, we again get a balance of forces, and we now have a relationship between the rate of strain, between the strain, the gradient of u0, and the stress, which involves history dependence. So let me take you through this. The stress, sigma, is a linear combination of the rate of strain, the strain, and this latent variable r, which I'll come to in a moment. U prime and E prime are constants, so there's no appearance of the small parameter epsilon. So this is then a model that's cheap to compute with. And the key thing here about this structure is that R satisfies a differential equation, which depends on the history of the rate of strain. And so this latent variable R is a surrogate that captures the historical dependence on the strain, the gradient of u0. So this example shows you that there are problems in physics where the recurrent neural operator structure that I wrote down at the beginning of the talk is very natural. I will recall the notation I used there. This is a function f of the strain, rate of strain, and a latent variable r. And the equation for r is a time-dependent equation with the right-hand side given by a function g, which depends on the latent variable r and on the history through the gradient of u0 and the history of the strain. And although this theorem only applies in the case of piecewise constant material properties, you can approximate any material properties that are sufficiently smooth by piecewise constants. And so this gives insight more generally than just the piecewise constant state case. And I want to emphasize that what you've seen here through the elimination of variables is the introduction of memory, and the recurrent neural operator is designed to capture that memory. So what we're interested in doing here is operator learning, where we want to find this mapping from the history of the strain to the stress. And just to recall the form of the recurrent neural operator, that is given through this pointwise function of the stress is a pointwise function f, meaning this applies pointwise in time and space to the strain, the rate of strain, and this latent variable r. And the latent variable r satisfies its own differential equation, which involves the strain and therefore captures the history of the strain. And an important thing to understand here is that a priori, we don't know the dimension of this memory variable. That too has to be learned as part of this neural operator learning procedure. Remember, this is an example where we know everything about the equation, and so it's a test. And I'm going to take you through it and show that it works, and then we're going to apply it, and you'll see that similar conclusions hold for a problem in plasticity where we do not have the theoretical understanding we have for this. So this first slide shows that we can correctly learn through the recurrent neural operator, we can correctly learn the response of the system. We train, here are some typical training strains. So we use these to generate, and of course there are thousands of them, but here are 3 typical ones. These are paths, they're functions of time. So we use strain histories like this, coupled with stress histories to train the model. And what you see here is a test. So we're showing the strains as a function of time. And on the right-hand side, there's a comparison between, and the comparison is such that we have we've learnt perfectly through the recurrent neural operator, we've learnt perfectly the relationship between stress and strain. So here you see the stress as a function of time for these 3 paths. And for each one of these responses, the stress as a function of time, there are in fact 2 curves. One is the true solution, and the other one is the one computed through the recurrent neural operator. And the key thing to appreciate is that they lie on top of each other. So we've successfully learnt this response of this system, and we've learnt what's called the homogenized constitutive model. Okay, but as I mentioned, part of this training involved determining the number of hidden variables. And I just want to show you the experiments here which test the response of the system and our training procedure as a function of the number of hidden variables. Let's just focus on the middle one here, which is for a specific setup. What you see here is that until you get to 4 hidden variables, the error keeps decreasing, but once you reach 4 hidden variables, both the train and the test errors saturate, and these are such that this means that we can approximate this system with 4 latent variables. One final thing that you see from this relates to the form of the model and also links back to something that Anima highlighted in her talk. What we're looking for are models which are invariant to discretization. And what you can see from this particular example, in which I'm going to compare in blue a poorly chosen recurrent neural operator, and I'll explain the axes in a moment, and in orange a well-chosen recurrent neural operator in terms of the variables that they depend upon. And what we're training at this particular value of the time step, which is a discretization of time, and we ask ourselves how well do we do if we use our model at different time steps. As Anima nicely explained, one of the goals of this function space perspective on learning is that we want things that transfer between different levels of discretization. What you see with this blue and poorly chosen form of architecture, of recurrent neural architecture, is that the errors are enormous and very sensitive to the choice of the time step. If the time step is increased by a very small amount, although you obtain excellent training error at this time step, when you use different time steps, you see enormous sensitivity and very poor behavior. So this is a useful method of testing the form of architecture and the dependence on variables and latent variables. Okay, how am I doing? How many minutes more? 3? So let me just say that everything I've said for the viscoelastic problem was testable because we have a theory. But we can now take that and apply it to more complicated problems. And again, if you want the slides, you have them. We've carried out exactly the same program for a plasticity model, which has a very similar form to viscoelasticity, but is more complex. And I want to just take you through these very quickly, because they have the same message that I've shown you in the viscoelastic case. But in this particular case, we do not know the true relationship between stress and strain. And so we're able to compute something that was uncomputable, hard to compute previously. All right, I'll just finish by making an observation about homogenization beyond what I've told you already for plasticity and viscoelasticity. So plasticity and viscoelasticity, I explained to you how we could learn function space dependence with respect to the historical dependence of the stress on the past history of the strain. That time dependence on the past is something that's intrinsic to the behavior of many problems in material science. What I did not learn was the dependence of the closure model, or the constitutive model as I called it, on the spatial properties of the material. So I wanted to just make a couple of observations about that, and this is work that we're currently engaged in and will result in a paper in the near future. So here I'm going to use the neural operator idea to learn a different mapping. You can apply this to elasticity, but I'll describe it in a slightly simpler setting. Again, there's going to be a problem with a small scale in it, which is a divergence form elliptic partial differential equation in which the solution unknown is u epsilon, and the solution is specified through data in the form of a function a epsilon, which is rapidly varying. The objective of homogenization, which is well understood in this case, is to determine an equation satisfied by u0, which approximates u epsilon, but in which the equation for u0 does not depend on this small scale and is therefore much more amenable to computation. So again, I'm going to talk about neural operator in a second. Again, the goal here is to work within the framework of understood mathematical or physical intuition about the equations and build in the neural operator into parts where we can enhance the underlying mathematical or physical structure. And I'm going to explain that to you in the last minute. So the theory of homogenization for this example says that there is an A0 such that, which does not depend on x, such that u0 approximates u epsilon and satisfies this equation, which is very computable because it does not involve the small scale epsilon. And the theory of homogenization comes with a prescription for how to compute A0, and it's in this panel here. You solve an equation that does not involve an epsilon and is therefore computable, rapidly and easily computable, for an unknown function chi, which then depends on this function a, which characterized the rapidly varying properties of the medium. And once one solves this equation for chi, you can perform an integration or quadrature to compute A0, which is the desired coefficient that appears in the equation for u0, which then does not involve an epsilon. So this mapping so this is a linear partial differential equation with solution chi, but its dependence on the function a varies with respect to this variable y, is nonlinear. So there's a nonlinear mapping from A to chi, and one can learn that using the theory of Nick Kavatsky from his thesis. It's possible to apply universal approximation theory to show that one can learn this mapping from A to chi. And therefore, by doing quadrature, you can recover A0. So this shows that it's possible to learn not only historical dependence, which involves time, but spatial dependence of constitutive models arising in mechanics. So I'd just like to finish there then by just let me leave this up here, but these are the conclusions which are just reiterating what I've been telling you over the last 45 minutes. Thank you for your attention.
Thank you. That was very interesting. I just had a very kind of simple question. You talked about a viscoelastic problem. Does your approach to all of this provide you with a wide range of solutions? I mean, you talk about, you know, sort of solving problems. I mean, would it do bending and torsion and you know, cantilevers?
Yes, thank you. So,
yeah, I mean, or is it just, you know, here's an airfoil at one specific speed and, you know, you just get that one solution, or you get a whole range of solutions? Yeah. That's kind of my...
So that's a really good question, and it's something we touched on in Anima's talk as well, which is how generalizable are the models that we learn. And there's always a limit, but we try and mitigate against that to the largest extent possible. In the context of these viscoelastic and plastic problems specifically, what we found empirically was that if we were to train on random paths, random stress histories, so we developed training data in which the stress histories had random temporal dependence. In so doing, we exposed the neural operator, in this case recurrent neural operator, to a bunch of different possible outcomes through this history. And in doing that, we got things that were much more generalizable and accurate than if we, for example, just trained on loading and unloading or cyclical forcing. But this is purely empirical, and it again comes to the question that I think is at the key for making this subject really have impact in science and engineering. We need to understand how to rigorously design experiments for the training of these problems so that they are as accurate as they can be beyond where you train them. And that remains open. Many of the problems where deep learning was initially successful, there's no control over the data. It's just scraped off the internet. Here we have a lot of control over the data, and so the design question about choosing the data to make the neural operator as accurate as possible is firstly, we have the possibility of doing it, and secondly, I think it's crucial to making this really have impact as a methodology. Thanks.
Thank you.
I have a question which is not related to the talk itself, but you mentioned the challenge in the theory and the fundamental theory to prove some error bounds on these approximate operators. It's just probably a wild idea, but is there any way to have experimental proofs, for example? Because you have the expensive FEM or any PDE solver that you can test against. Are there any ways to prove experimentally some error bounds on these neural operators?
And do you mean actually prove? So do you mean to use data to...
To an extent, I'm understanding it's super hard. So to an extent, to prove any error bounds.
So I think no is the answer at this current point in time. I think that there are, in analysis, there are a small smattering of results which are computer assisted. So for example, proof of chaos in the Lorentz equations rests on a computer assisted proof. There's recent work here by Tom Howe on blow up in the Euler equations, which has a portion of the proof that relies on a computer assisted part of it. But in general, in analysis, it's very hard to have computer-assisted proofs. There are parts of number theory where there are starting to be really rigorous computer programs that instantiate proofs. And I think we'll see more of that in that part of mathematics. But I think in analysis, it's really difficult and will be very specific for the foreseeable future.
Understand.
But thanks. And nonetheless, the empirical evidence of data is really, really important.
Yeah, I'm sure it's practically applicable already, right?
Hi. Several of the PDEs that you and Anima are studying are known to have non-smooth solutions, like nonlinear hyperbolic terms.
Yeah.
How robust are your techniques to these type of situations?
Yeah, so there are a number of papers by myself and others, including the Carniadakis group in Brown, which look specifically at the advection equation, linear advection equation, precisely because ironically, even though it's such a simple equation, it's one of the hardest equations to compute the solution for, not just by this method, but by standard PDE methods. And
or Burger's equation.
And Burger's equation. So I think the answer is that discontinuities provide examples of things where you can break this methodology, but there are a number of tailored methods which try and overcome this by, for example, allowing to learn rescalings which enable you to pick up discontinuities as part of the training procedure. So it's definitely a challenge for this field, and there is thinking going into how to go about doing it, but definitely you can break what I've shown you today by examples of that type. Thanks.
Hello, Professor. Thank you for the talk. I just had several questions, basically, but I'll just keep it short, very short. So my first question is basically on the approximation. So you said that's the supreme, if you go back to the slide on like the universal approximation. Just some math I was kind of worried about. Exactly. So this is defined, the supreme norm is defined over a compact set. So I'm assuming if this function E, is E continuous over here in this sense, then it would just be the maximum norm, right? Because of the...
Well, so I haven't specified, so what I'm being a bit loose about what I mean by compact, so because I haven't told you exactly what I meant. Yeah. We have the input space E.
Sure.
And so that theorem works on a compact subset of E. Yes. So in answer to your specific question, if E, for example, comprised continuous functions, then the compact subset might involve functions where several derivatives are continuous. Or if E is square integrable functions, then a compact subset might be a unit ball of functions where the first derivative is square integrable. So it's a very general. The results are very general, okay. And they use compactness for the reason that compactness is essentially, generally speaking, a methodology to enable finite dimensional approximation.
Okay. Then my second question was on GPs, basically. So I think GPs is a really good topic because you have that, when you're using a kernel method, you can go to this beautiful RKHS and everything makes sense well over there. And I was thinking, so I don't see that you have done experiments based on that, but on the RNO topic, could you like maybe explain a bit how you could use GP to solve instead of using...
Yes, sorry, going the wrong way.
Yes, this one. So F and G, instead of using neural networks, you use these beautiful kernel methods, basically. And what type of kernel would you choose? And could you just give me some brief?
Yeah, sure. So firstly, let me say that Houman who's talking next, is the real expert on GPs. And both he and I agree with you about the potential for GPs because of the theory that they come with. And there are random features methods which build on them that we have some expertise in here as well. So I share your enthusiasm for GP-based methods, in particular for the possibility that they will come with theory much more quickly than the neural operator. What I would say about this, the high level, is that this architecture, the important thing about it, has got nothing to do with how you approximate F and G. So it's really got nothing to do with neural networks. Okay. The important thing about this architecture is that the recurrent structure is a way of encoding memory through a differential equation and mapping it through the latent variable R into this function F. We know that we can do pretty well with neural networks in approximating Euclidean functions F and G, which these are, but you can also do really well with GPs. And I'm sure you could do just as well in everything I showed you with viscoelasticity and plasticity if you replace the F and G learning with GPs. And indeed, that is going to lead to a better theory right off the bat. So,
thank you. And then my last question, I'm sorry if anyone else has a question. But yeah, my last question is, so could you go to the slide where you had the inner product of the characteristic, I think 1 and R. I do not know what that inner product, how is it defined? Could you maybe a bit clarify that?
Yeah.
One of my questions.
Yes. So sorry, I should have explained this notation. As I mentioned, we don't know the dimension of R, so R is vector valued. Sure. But once you've determined the dimension, 1 comma R just means I'm summing all of so each component of the vector of R. So R is a vector function of T. So let's say it has 2 components. There'll be an R1 of T and an R2 of T. Now at a fixed time T, I just add R1 of T to R2 of T.
I see.
The reason that I can put 1 there as opposed to weights is that the weights are taken care of by the coefficients that occur down here in this specific structure.
Yeah, And I was actually very curious about his point because when I took PDs, I remember like learning about like Berger's equation and all about these shockwave solutions which occur. And I'm assuming these methods are robust too. Like I think you answered that, but do they care about, or do they take care of these shockwave type of solutions?
No, they don't, but there is work to generalize beyond what I've described.
Okay.
And that was the answer to the previous question.
Yeah, makes sense. And I'm pretty sure that all these PDs are well posed, right? Like in the sense, there is like existence uniqueness theorem,
well,
because these are conservation laws, I guess.
For everything in this talk, except the plasticity problem, where there is some limit to the theory. But for the Navier-Stokes, the viscoelasticity, there is a complete theory of well-posedness.
Okay, thank you so much for the question.
Thanks.
Thank you for the talk. I have the question about the universal approximation theorem. So you showed it for like general neural operators, but there are different architectures already for neural operators.
Yeah.
Is there any difference also in comparison if you compare FNO to recurrent neural operator, how they converge towards each other?
Yes, thanks. It's a really good question. So firstly, this really isn't a theorem. It's just indicating the type of theorems that exist. And if you follow up these references, you'll see exactly what has been done for these different architectures like DeepONet, PCANet, the neural operators, and the RNONet. The difference between them, I think, so a major problem with this whole field is that these universal approximation theorems just assert the existence of a choice of parameters where you can achieve a given error. The key question is how much does it cost you, either in terms of data to train or to evaluate the method, evaluate the approximation to get a given error epsilon. So that's the subject of cursive dimensionality. That's well understood for the numerical solution of partial differential equations, and that's why it's such a beautiful field that's had such a big impact on science and engineering. It's not yet well understood in this area, but there are, and I highlight here 2 papers which look at the cursive dimensionality for some specific PDE problems and show that it can be beaten. What do I mean here by the cursive dimensionality? I'm saying here that we have the cursive dimensionality if the cost of evaluating the map to achieve a given error epsilon grows faster than algebraically with respect to the inverse of epsilon. There are examples you can show where that's beaten, so you get algebraic dependence on 1 over epsilon in terms of cost. And if you follow these papers, you'll see examples of where that is done. But it's very far from being a complete theory. It's not a complete theory for numerical PDE either, but it's way less developed here. So that's where research is needed in that question.
Thank you.
I have a question regarding the data design. How did you, for the examples you show, how did you generate your examples that you trained the neural network on?
Yeah. Thank you. So as I said earlier, data design is an opportunity in this field because we can do it as opposed to scraping data off the internet. And secondly, it's very important. But there's no systematic answer here. But it's an interesting question to try and develop active learning methods, for example, to do this. Specifically, there are 2 things. One, I think I mentioned in answer to an earlier question, that the first question, that we used random, in the plasticity and viscoelasticity, we used random straining paths because that exposed the problem to the most variation and empirically worked the best, intuitive, and we have empirical evidence that it worked well. In the case of the GP, we chose the design points by, in a sense, we're trying to solve a parameter calibration problem here in the climate model. In a sense, we pre-solved that problem by using ensemble Kalman methods, which are very efficient, but they don't give a full uncertainty quantification. But we did pre-solve with that methodology, and that gave us the basis for design points that are used within these kernels. And that's a methodology which I am developing theory for with collaborators in Finland and Edinburgh. We have a paper that we've just completed which tries to understand what a good choice for these is and how that impacts the accuracy of the approximation. But again, this is something that's in its infancy, lots of space for analysis and methodology to be developed.
Thanks. And maybe with regards to the architectures you talked about here, like maybe regarding robustness, is there a big difference if you take, like, for example, noisy data or exact data to train your neural network? Is there like a big difference with regards to robustness for the different architecture?
Yeah, I don't have anything to say about that because I don't think there's been enough consistent, careful experiments done to answer it. You can find people who'll tell you something about that, but I don't think there's a really careful study of it. One thing I would say is that the ensemble Kalman method is incredibly robust, and that's why we use it to find these design points. And there is some theory about that. But generally, robustness is not for the neural operator stuff, and more study is needed.
Okay,
and
thank
analysis.
you.
Thanks.
Thanks.
Thanks, Andrew. I have a question about the recurrent formulation that you had.
Yes.
You set R0 to 0, the initial condition of the hidden state, and I'm just curious are there limitations to making this choice? What kinds of systems can you express with this, and what can't you express?
Thank you, that's a good question. So in this case, for the viscoelastic problem, we know the existence of an F and G, and they can be instantiated with R0 equals 0. And so in that case, we can prove that within this class of F and G, it is possible to approximate arbitrarily well the truth. And empirically, we find that we can do well on other problems by fixing R0 equals 0. But as you well know, from other problems you have tried to approximate using this recurrent structure, it can be very difficult in general. So here I would only limit our success to those problems in material science and plasticity and viscoelasticity that I've shown. And in that case, the initialization was not key to making this work. And by the way, I should have acknowledged you. Matt had a big impact on this area because he's thought a lot about these. Matt is the person asking the question. Thank you.
Can I ask also a question about the Euler kink in time? You had the
Which
integrator.
kink?
So you had the test error versus time step.
Was that on elasticity?
Yeah.
Okay, hang on. Get there.
Yes.
This kink.
So I assume that as it goes left, it gets worse, but that's an undesirable pathology in some sense.
It's undesirable, but they're still accurate. This is what's really undesirable, right? You slightly increase the time step and the error becomes order 1. And that's because the model form is not expressive enough to capture the truth. And so you can train it at a particular, you can overfit it essentially at a particular time step, but you didn't really learn an intrinsic continuous time model. And so when you try and use it at a different time step, because the continuous time model you trained is not expressive enough to capture the truth, you get a bad error. That's really what's going on.
And I guess to a lesser extent, that's still happening with the Euler. But do you think that this pathology would reduce if you trained on a finer resolution and/or you use a higher fidelity integrator like Runge-Kutta? Like, could you flatten this and make it look correct?
You might flatten this part, and this slope you might be able to change. We don't completely understand that slope, but I think what you're saying would affect these parts, but not this.
Yeah. Okay. Thank you.
Thanks.
I just had a question about these, the fast oscillating functions and how far down you can go with homogenization. For example, if you were given the lattice structure of a material at the discrete level by a chemist or a material scientist, would the problem of estimating the hysteresis curve and the bulk properties of the material just from that model be feasible here?
No. So thank you. That's a very good question. So homogenization certainly enables you to go from one scale to another, but if you think of the material at a quantum level, this is not described by this variation in epsilon. There are alternative theories, whole hierarchies of models which go between different scales. So if you start at the quantum description of material, then one can go from that up to the scale in which you would see material properties of the type in the upper panel here, which vary rapidly, and then the mathematical problem of homogenizing to get a problem that's accurate is yet up another scale. So there are many, many scales present. But the beauty of material science in comparison with turbulence is that there are many problems where there are clear scale separations. So this methodology and others relating, say, quantum to continuum, are most effective when there's a clear scale separation, which there is in many of these problems, and which there isn't in turbulence, which was one of the reasons it's so difficult.
So this all happens in the continuum model. Okay.
This is all in the continuum, yeah. But there are relevant problems where also neural operator can be useful about transitioning between, say, quantum and continuum.
That's been
or
done.
Quantum and atomistic and then continuum. Thank you. Thanks. Okay, welcome back, everyone. So final talk this morning is Houman, who's going to talk about solving and learning nonlinear PDEs using Gaussian processes.
Thank you, Andrew. Thanks for the introduction. So as Andrew mentioned, the main focus of my talk will be on solving and learning nonlinear partial differential equations with Gaussian processes. Now, there are two main learning approaches to solving PDEs. Approaches based on artificial neural networks and approaches based on Gaussian processes. And while approaches based on Gaussian processes are more theoretically well-founded and have a long history of interplays with numerical approximation, these approaches were essentially limited to linear/quasi-linear/time-dependent PDEs. And what I'm going to present in the first part of this talk will essentially be a generalization of these Gaussian process-based approaches to arbitrary nonlinear PDEs. And this generalization is a joint work with Yifan Chen, Baghdad Hosseini, and Andrew Stuart. And the method that we have obtained from this generalization has a few desirable properties. It is probably convergent for forward problems. It is interpretable and amenable to numerical analysis. You can use it to solve both forward and inverse problems. It inherits the near-linear complexity of state-of-the-art solvers for dense kernel matrices. It comes with UQ estimates that are compatible with a UQ pipeline. It comes with rigorous a priori error estimates, and it extends to high-dimensional parametrized PDEs. Now, the proposed method can be applied to arbitrary nonlinear PDEs, but for ease of presentation, I'm going to describe it first for this particular nonlinear elliptic PDE, in which f, g, and tau are assumed to be continuous, so that this PDE has a unique, strong, or classical solution. So the nonlinearity in this PDE is tau, and as an example, you can take tau of u to be u cubed. Now, given a kernel K defined on a whole space, the proposed method is to approximate the solution U dagger of the PDE with a minimizer UN of the following nonlinear optimal recovery problem, in which the quantity to be minimized is the RKHS norm of the function U as defined by that kernel K, and the constraints are requiring U to satisfy the PDE at a finite number of collocation points in the interior of the domain and on its boundary. Then we have the following theorem. Assume that the kernel K is chosen so that the solution of the PDE belongs to the RKHS space defined by the kernel K. Assume that that RKHS space has enough regularity to be continuously embedded in some sublet space HS for some S greater than the dimension of the space over 2 plus the order of the PDE, which is 2 here. We need that condition to ensure that the PDE is defined strongly for the elements of the RKHS. And assume that the field distance between collocation points goes to 0 as n goes to infinity. Then, as the number n of those collocation points goes to infinity, the approximant obtained by the proposed kernel method converges towards the solution of the PDE, where the convergence holds pointwise in the domain and in the subspace HT for all t smaller than s. And this theorem generalizes to arbitrary nonlinear PDEs, and I refer to the following paper for its general form. So this theorem is essentially saying that the proposed method is guaranteed to converge for an arbitrary nonlinear PDE, provided that the solution belongs to the RKHS space defined by the kernel K, provided that that kernel has enough regularity so that the underlying PDE is defined strongly for the element of the RKHS, and provided that your field distance between collocation points goes to 0. Now, I'm going to show you the proof of that theorem, not only because it is very simple and it extends to arbitrary nonlinear PDEs, but also because it reveals a simple fundamental mechanism supporting kernel methods. So the proof is articulated as follows. Because U dagger is the solution of our PDE, and because U dagger belongs to the RKHS space defined by the kernel K, U dagger must satisfy the optimization constraints of our nonlinear optimal recovery problem. Because UN is a minimizer of our nonlinear optimal recovery problem, the RKHS norm of UN must be smaller than the RKHS norm of U dagger. Now, because the RKHS space defined by the kernel K is continuously embedded in HS, we know that for all functions V, the HS norm of V must be bounded by some constant C times the RKHS norm of V. Therefore, the HS norm of UN must be bounded uniformly in N by a constant C times the RKHS norm of the solution. And because the sublet space HS is compactly embedded in the HT for all T sandwiched between S and D over 2 plus 2, we know that UN is going to converge towards some limit in HT and in C2 along some subsequence. Now, because UN satisfies the PDE along that subsequence at collocation points, and because the field distance between collocation points goes to 0 as their number goes to infinity, we deduce that the limit must satisfy the PDE everywhere, and because the solution is unique, the limit must be the solution, and because the limit is independent from the subsequence, the whole sequence is converging, right? So you saw that the proof of convergence is very simple. Okay. Now, for the practical implementation of this method, this infinite dimensional optimization problem must be first reduced to a finite dimensional one. And the first step in doing so is to introduce those slack variables Z1 and Z2 corresponding to the values of U and of its Laplacian at collocation points. And then you minimize over U before minimizing over Z's, right? Now, if you look at this optimization, if you minimize over U before minimizing over Z, you realize that this inner loop is a linear optimal recovery problem for which you have a representative formula for U, which I am now going to unpack. So in that formula, Z is a vector obtained by concatenating Z1 and Z2 that again correspond to the values of U and of its Laplacian at the collocation points. Phi is a vector obtained by combining the vectors Phi1 and Phi2, whose entries are masses of Diracs centered at the collocation points, or masses of Diracs centered at the collocation points composed with the Laplacian. Kx phi is a vector obtained by integrating the entries of that vector phi against the kernel K at a particular point x. And K phi phi is a matrix obtained by integrating the kernel K against those entries of phi that are called phi I and phi j. So observe that to evaluate Kx phi and K phi phi, you must evaluate pointwise your kernel K and its higher order derivatives. And this is the same thing for this matrix K phi phi. Okay, now if you take, so this representative formula is essentially telling us that we can reduce the identification of this unknown function U to the identification of this slack variable Z. And if we take that representative formula and we plug it back into our previous optimization problem, we get a reduction of the original optimization problem to one that only depends on Z, that is computationally tractable because Z is finite dimensional. Now, to solve this quadratic optimization problem in Z, that is non-linearly constrained, we use the constraints to eliminate one of the optimization variables, which are the entries of this vector Z2, which again correspond to the Laplacian of the solution U at collocation points. And we reduce this quadratic non-linearly constrained optimization problem to an unconstrained non-quadratic optimization problem. And to solve that unconstrained optimization problem, we use a variant of the Gauss-Newton algorithm. Now, the Gauss-Newton algorithm is an iterative algorithm that successively approximates the minimizer of the following problem by successively linearizing the nonlinearity tau in this problem around the previous approximation of the solution. And at each step, you simply end up solving a quadratic optimization problem to get the next approximation. Now, in practice, this Gauss-Newton iteration converges in 2 to 7 steps. 2 steps for that particular nonlinear elliptic PDE, which means that the proposed method inherits the complexity of fast linear solvers for dense kernel matrices. And I will show later on that you can achieve near linear complexity through a generalization of a result in this paper, and this generalization is a joint work with Yifan Chen and Florian Schaffer. Okay. So the following figures illustrate and compare the convergence of the proposed method against the finite difference method. So you get convergence to machine precision, which is something that is oftentimes hard to get with deep learning methods, but you can get it with kernel methods and Gaussian process methods. So Gaussian process methods are somehow located in between deep learning methods and traditional methods. And I will make the claim that if you use this kind of methods, you kind of get the best of both worlds. You get the guarantees of traditional methods, and you get the flexibility of learning methods. And here again, here we have used the following Gaussian kernel to obtain those plots. Okay, so as I mentioned, the proposed method and its theorems generalized to arbitrary nonlinear PDEs. And what you see here is an application to the approximation of the solution of the Burger's equation when using the following kernel. And this kernel has been chosen to be anisotropic to capture the underlying shock being developed in space but not in time. So again, the table shows the convergence rate as a function of the number of collocation points. This is where those collocation points are located. You can pick them at random in the interior of the domain and on the boundary. This is a contour plot of the errors. The error is mainly centered around the singularity. And these plots are showing the true solution and the numerical solution for different times. And in eyeball norm, you get the solution. Okay. This is another application to Eichhorn's equation when using the following isotropic Gaussian kernel. This table is showing the convergence as a function of number of collocation points in L2 norm and in sup norm. Here, the Gauss-Newton iteration converges in about 6 steps. So this PDE is harder to solve than the previous ones. Okay, as I mentioned earlier, the proposed method can be generalized to solving inverse problems, that is learning PDEs, for instance. And in the following application, we're going to approximate the unknown solution U and the unknown function A serving as a coefficient for this PDE, given the observation of the right-hand side F at the blue collocation points, given the observation of the boundary condition G at the orange collocation points located on the boundary, and given the observation of the solution U at the data measurement points, which are colored in pink here. So the proposed generalization is to simply approximate U and A by minimizing the sum of the squares of their RKHS norms with possibly two different kernels, subject to the PDE being satisfied at the blue collocation points in the interior of the domain, at the orange collocation points on the boundary of the domain, and subject to our measurement or observation of the value of the solution U at the data measurement points, which are again colored in pink here. So the proposed figures are showing the true solution A, the recovered solution A, so the true coefficient A and the recovered coefficient A, and the true solution U, and the recovered solution U. And the recovery is not exact because we only have 40 measurement points or data points on the solution U. The Gauss-Newton iteration converges in about 6 steps, which means that, again, the method inherits the near-linear complexity of inverting dense Kendall matrices, which is much, much faster than using MCMC methods. Now, another difference with MCMC methods is that here we are not iterating between solving a forward problem and solving an inverse problem. We are solving both at the same time. Okay, now I'm going to discuss a priori error estimates. And this part is a joint work with Paul Battier, Yifan Chen, Bamdad Hosseini, and Andrew Stuart. To do so, I'm going to consider an arbitrary nonlinear PDE written in general form. So here, P is our interior differential operator, and B is our boundary operator. Recall that the proposed method is to approximate the solution U dagger of this PDE with a function UN defined as a minimizer of the following optimal recovery problem, in which you minimize the RKHS norm of U, subject to U satisfying the PDE at a finite number of collocation points in the interior of the domain and on the boundary. Then we have the following theorem. Assume that the domain is compact and with Lipschitz boundary. And assume that the forward and solution operators defined by the PDE are locally continuous. I will unpack what I mean there. Assume that the RKHS space defined by the kernel K is continuously embedded in the subspace HL. And this is what we mean by this continuous embedding. Then the approximation error of the proposed method is bounded by some constant C times some power of the field distance between collocation points times the RKHS norm of the solution of the PDE. And you can think of this power as a regularity parameter essentially representing the difference between the regularity of the solution U and the weakness of the norm that you use to measure your error, right? So as an example, you can think of gamma as being the difference between L and S, where L is the parameter reflecting, again, the regularity of the solution, and S is the parameter reflecting the strength of the norm that we are using to quantify our error estimates. Now, I'm going to show you the proof of this theorem, not only because it is very simple, but also because it, again, reveals a fundamental mechanism supporting kernel methods. And you can also generalize this proof to neural networks, except from one point that is not explicit in neural networks, and I will show you what that point is. So for ease of presentation, I'm going to ignore the boundary, and I'm going to assume global stability of my forward and my solution operator. And I'm going to use abstract norms instead of Sobolev norms. Okay, so because the solution operator is stable, some one norm of the difference between the solution of the PDE and our numerical solution UN is bounded by some constant C times some two norm of the difference between P of U dagger, the solution of the PDE, and P of UN, our numerical solution, where remember that P is our differential operator. Now, because the solution of the PDE and our numerical approximant both satisfy the PDE at collocation points, this difference between P of U dagger and P of UN is equal to 0 at collocation points. Therefore, if we use something called a sampling inequality or sampling error estimates, which are traditionally equalities that you find with kernel methods, then we get that this two norm of this difference between P of U dagger and P of UN is bounded by some constant C times some power of the field distance between collocation points times some stronger norm on this difference between P of the solution of the PDE and P of our numerical approximant. Now, this power gamma is directly related to the difference in strength between this 3 norm and this 2 norm. So if those are Sobolev space norms, and if this is an HS norm and this is an HS prime norm, this gamma will simply be S minus S prime. Okay. Now, because the forward operator is stable, this 3 norm on the difference between P of the solution of the PDE and P of our numerical approximant is bounded by some constant C times some 4 norm on the difference between the between the solution of the PDE and our numerical approximant. Now, if we use the continuous embedding of the RKHS defined by the kernel K, then we get that this 4 norm on the difference between U dagger and UN is bounded by constant C times the RKHS norm of the difference between U dagger and UN. Now, and this is really where we are using explicitly the fact that we are using a kernel method. Because we are using a nonlinear optimal recovery problem to recover the solution of the PDE, we know that the RKHS norm of our approximant is smaller than the RKHS norm of the solution of the PDE. And as a consequence, we deduce that this RKHS norm of the difference between U dagger and UN is bounded by 2 times the RKHS norm of the solution of the PDE. And if we put everything together, we conclude that this 1 norm of the difference between U dagger and UN is bounded by constant C times some power of the field distance between collocation points times the RKHS norm of the solution of the PDE. So again, you can try to apply this theorem to neural networks if you want. What you will have to show is that some norm of your solution does not blow up as you try to learn that solution. This comes for free with kernel methods. This is something that you will have to show for neural network methods. Okay, now if you take these abstract norms 1, 2, 3, and 4, and you replace them by appropriate Sobolev norms, then you get the precise statement of this original theorem, but where we have a precise statement in terms of Sobolev spaces for what we mean by the forward and solution operators being locally continuous. Okay. Furthermore, if you assume the collocation points to be homogeneously distributed in space, and if you express your a priori error estimates as a function of this number n of collocation points, then you get a bound on your error that exhibits a trade-off between dimension and regularity. In particular, if you make your problem very regular, and you have two ways of making your problem very regular. You either make the solution very regular, or you make the norm in which you measure your error very weak. If you make your problem very regular, then you realize that you get a bound that does not depend on dimension, and then you see no curse of dimensionality. And if you look at most of the recent methods proposed for understanding the breaking of the curse of dimensionality in deep learning, so these methods are typically based on Baron spaces or some functional spaces, you will see that these function spaces are equivalent to very, very regular subgroup spaces, which is why you don't see the curse of dimensionality. Now, because of this trade-off, showing that a numerical method remains accurate for a high-dimensional PDE may not be an indication that it is breaking the curse of dimensionality, but simply an indication that the problem being solved is very regular. To illustrate this point, we are going to consider the following Hamilton-Jacobi-Bellman PDE in dimension 100. This PDE was used as a benchmark in the following paper by Han and Jensen in 2017 to support the point that neural networks are breaking the curse of dimensionality in solving high-dimensional PDEs. And we are going to compare the accuracy obtained in this paper with a neural network method with the accuracy obtained with the proposed kernel-based method with a Gaussian kernel. And what you can see is that they have comparable accuracies, but the kernel method is much, much faster. And most importantly, the kernel achieving this accuracy is a Gaussian kernel with a very, very large length parameter. So the size of the domain is 1, and the length scale here is 200, which suggests that the solution of the PDE is not only very regular, it is also nearly constant. So I'm also showing this example to stress the importance of your deep learning method, the importance of benchmarking your deep learning methods against kernel methods whenever you are using deep learning methods in scientific computing. If you don't benchmark them against kernel methods, then you don't know if the deep part of your method is doing anything beyond adding complexity. Now, speaking of complexity, I'm now going to discuss the complexity of the proposed method. And again, this part is a joint work with Yifan Chen and Florian Schaffer. Now, recall that the complexity bottleneck of the proposed method is that of evaluating, storing, and possibly inverting this dense kernel matrix, K-phi, whose entries are pointwise evaluations of the kernel K and its higher order derivatives at the collocation points. Now, because this matrix is typically dense, if you just try to evaluate it or store it, you're already going to pay n squared. But although this matrix is dense, for a large class of kernels, including the Matern class of kernels, you can perform these operations in near linear complexity with a generalization of the sparse Zariski factorization algorithm found in this paper. And again, this generalization is a joint work with Yifan Chen and Florian Schaffer. So the result goes like this. If your kernel K is the Green's function of some elliptic PDE, and again, the Matern class of kernels satisfy this assumption, then you can reorder the entries of that measurement vector phi. So recall that those entries are essentially delta Dirac functions at the collocation points composed with derivative operations. So you can reorder the entries of your measurements, which is equivalent to reordering the columns and rows of your matrix K-phi, so that from the computation of n log d n over epsilon entries of K-phi, you can compute an upper triangular matrix U with n log d n over epsilon non-zero entries in n log 2d n over epsilon operations, so that UU transpose minus 1 is an epsilon accurate approximation of the matrix K phi. Okay? Now, the idea behind this result is that the Cholesky factors of the inverse of K phi depend on the ordering of the entries of phi. And if you use an arbitrary or lexicographic ordering, then you get dense Cholesky factors. But if you use something that I will call the hierarchical ordering, and I will unpack what I mean, then you get sparse Cholesky factors. And by sparse, I mean that most of the entries of these matrices will be close to 0, and because they will be close to 0, you will be able to approximate them well with matrices that are really sparse, meaning most of the entries are actually going to be 0. So by hierarchical ordering, I mean ordering the Diracs in your measurements first, using a max-min ordering. So this max-min ordering is essentially going to place points that are as far as possible from each other, and then it's going to refine the placement of these points. And we're going to order the higher order derivatives measurements next. So we're going to essentially treat them as fine scales. Now, why do you get sparse Cholesky factors with this hierarchical ordering? So to understand this result is based on two observations. So first, the Cholesky factors of the precision matrix are directly related to the conditional correlations of the Gaussian process Xi, having mean 0 and kernel K. Next, because of the screening effect, which can be summarized as nearby observations reduce correlations with more distant observations, these conditional correlations are sparse if you use this hierarchical ordering. This is really what is causing the acceleration. Okay. Now, what I would like to show is that you can see the proposed method for solving and learning PDEs as part of a more general framework aimed at using GPs to compute computational graphs. So to describe this, consider our original PDE and observe that U is a solution of this PDE if and only if U solves is the unknown function solving the following computational graph, in which nodes represent variables and edges are directed and they represent functions, with known functions colored in black and unknown functions colored in red, right? And you can see that the proposed approach is essentially equivalent to completing the graph by replacing the unknown function U with the Gaussian process and computing its map estimator given the data, which corresponds to the observation of F and G at collocation points. Now, similarly, the proposed solution for this inverse problem can be formulated as identifying the unknown functions A and U in the following computational graph, okay? So the proposed approach is then equivalent to completing this graph by replacing the unknown functions U and A with independent Gaussian processes and computing their map estimator given the data, which corresponds to the observation of the right-hand side of the PDE at the interior collocation points, the observation of the boundary at the boundary collocation points, and the observation of U at the data points. Okay. Now, what I just described is not limited to solving and learning PDEs. In fact, most problems in computational sciences and engineering can also be formulated as completing computational graphs representing dependencies between functions and variables. And they can be solved in a similar manner by replacing unknown functions by Gaussian processes and computing their map or empirical Bayes estimator given the data. These problems include climate/weather modeling and forecasting, or system identification, learning SDEs, dimension reduction, learning Hamiltonian systems, deep learning, etc. How much time do I have left? 10 minutes, thank you. Okay, so the proposed common solution to all these problems can be seen as part of a generalization of Gaussian process regression from approximating single input-output functions to approximating multiple functions and variables whose dependencies are represented by a computational graph. And what I'm now going to do is to describe this generalization from an abstract perspective, show you an application to system identification, and give you some motivations for developing this kind of framework. Okay. So what we mean by computational graph is a graph where nodes represent variables and edges are directed and they represent functions. So for instance, the following diagram represents the identity xj being equal to f of xi. We are going to interpret multiple incoming arrows as a sum, so the following diagram is interpreted as xj being equal to f of xi plus g of xk plus h of xl. Now we're going to use square nodes to represent primary variables and round nodes to represent variables obtained through the concatenation of other variables. So the following diagram is interpreted as the variable z being equal to the concatenation of the variables x and y. And we interpret the following diagram as the following equations holding true. Now, for that particular diagram or graph, the entries of this vector x are the variables of the graph. The entries of this vector f are the functions of the graph. And we say that the vector x is a sample from the graph if its entries satisfy the functional dependencies imposed by the graph. Now, if you are given n samples from the graph with n equals 3 here, then you can see those samples as the rows of some matrix X that here has 3 rows because we have 3 samples and 6 columns because we have 6 variables. Now, for each sample, you may not observe all the variables in that specific sample, and we are going to indicate which ones we observe using this other Boolean matrix M, whose entry Si is 1 if variable I is measured in sample S, and 0 if variable I is not measured in sample S. So for instance, those are the observed variables in sample 1. Those are the observed variables in sample 2. And those are the observed variables in sample 3. And using Python programming notations, we're going to write x of m for the subset of the entries of the matrix X that are actually observed. Now consider the following problem, which we call a computational graph completion problem. Assume that some of the functions of the graph are unknown. We're going to color those unknown functions in red. Then, given the observed entries of the matrix X, approximate the unknown functions and recover the unobserved variables or unobserved entries of this matrix X. Observe that this problem combines a regression problem that is approximating the unknown functions with a data imputation problem or matrix completion problem that is completing this matrix X. Now, our solution is going to be to replace all the unknown functions of the graph with independent Gaussian processes. You could also take them to be correlated, but now we take them to be independent. And then recover all these unknown functions by computing the map or empirical bias estimator of all these unknown functions given the available data. So this is equivalent to approximating these unknown functions f by minimizing the following nonlinear optimal recovery problem, in which the optimization variables are these unknown functions f, this variable z that is a candidate for a matrix X, and these variables y, which correspond to the output of all the functions of the graph. The kernels used here are assumed to be given a priori, but you could also learn them from data. The first constraint is defining these variables y as the output of all the functions of the graph. The second and third constraints are imposing the connectivity or structure of the graph. The last constraint is the constraint imposed by the data. And again, this is an infinite dimensional optimization problem, but if you fix the slack variables z and y and you minimize over the unknown functions first, you get a representative formula for these unknown functions, and if you plug that formula back in your original optimization problem, you get a computationally tractable optimization problem over y and z that is finite dimensional. And as an example of application, we're going to consider the identification of a nonlinear electric circuit in which the resistance, inductances, and capacitances are assumed to be unknown and nonlinear functions of currents and voltages. And all the voltages and currents in the circuit are assumed to be unknown functions of time. So we run the circuit between time 0 and time 10, and at times Ts equals to S over 10 for S going from 0 to 99. We observe a random subset of the values of the variables representing the state of the system. So for example, we're going to observe the voltage V1 at these 7 points in time. And given those measurements, we want to approximate all the unknown functions given voltages and currents as a function of time, and giving us the inductance and resistance as a function of current, and giving us capacitance as a function of voltage. Now, those are our actual measurements, and you see that they are very sparse. So you cannot solve this problem by simply regressing any of those functions independently from the others. To solve this problem, you have to use the information shared by all these functions. And to describe this, I'm going to write x for the variables of the system. So those are the entries of this vector x. I have about 14 of them. Those variables are not independent. They are related through functional dependencies between them that are essentially the Kirchhoff laws for this nonlinear electric circuit. We can represent these non-functional dependencies between variables as a computational graph in which variables are nodes and edges are directed and they represent functions, with unknown functions colored in red and non-functions colored in black. Our data comes in the form of a subset of the observation of those variables, a subset of those variables at different times, at different points in time, and these are essentially a subset of the entries of that matrix X. And again, the solution is to simply replace these unknown functions by GPs and compute their map estimator. And if you do that, this is what you get. So you get something that is surprisingly accurate, given that the data was quite scarce. And the reason why you get accuracy is because you're exploiting these dependencies between functions and variables. Okay, now I'm going to finish by giving some motivation for developing such a framework. This was life before AutoCAD. This is life after AutoCAD. Computing square root of 2 is complex if you try to do it by hand, but simple if you use a pocket calculator. Calculating an amortization schedule is complex if you try to do it by hand, but simple if you use an Excel sheet. Why? Because the complexity of a problem is relative to our ability to decompose it by reasoning through simple concepts, encapsulating and abstracting away its technicalities. And if you automate the resolution of those technicalities, then you're only left with manipulating high-level concepts, and you're therefore free to perform tasks of significantly higher importance of complexity. The automation of calculus is an illustration of such a paradigm shift. And the question that I would like to ask is a similar transformation possible for computational sciences and engineering? And the reason why we may think that the answer might be yes is because most CSC problems can actually be formulated as completing a computational graph, representing functional dependencies between known and unknown functions and variables. And since the completion process can be reduced to an algorithm, as one solves square root of 2 on a pocket calculator without thinking about it, you could, in a similar way, in principle, solve a complex CSC problem by drawing a diagram and letting a machine complete the diagram for you. Thanks for your attention. Okay.
Okay, questions for Houman, please.
Hi, so the first question I would have is maybe with respect to the example for inverse problems you talked about. Did you assume any statistical noise, or did you take the exact solution and observe it at discrete points?
You mean for the electric circuit or the PDE examples?
PDE.
So in the PDE example, we didn't assume any noise in the observation of F or G. In practice, if you use a misspecified kernel, meaning that if you use a Gaussian kernel but your solution is not analytic, then you have to add a nugget, which is equivalent to adding a little bit of noise.
Okay.
But if you use a Matten kernel, which is well specified, then you don't need to add that noise.
Okay.
So you can use noise to represent misspecification in your kernel.
Mm-hmm. Okay. Thank you. I have another question in regards with also with inverse problems. So as I understand, what you get in the end by the algorithm you talked about is an estimator for the parameter you recover and also you. So you said you kind of solve forward and inverse problem at the same time.
Yes.
But do you get any result? So you compare it to MCMC methods. So like in MCMC methods, you can also get uncertainty quantification because you sample from the posterior, for example.
Yes.
Is there anything similar for this kind of procedure?
Yes. So in principle, you can not just get the map estimator, but also the whole posterior distribution. And this is an ongoing joint work with Andrew.
Oh, okay. 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 Thank you. And okay, I have one question regarding the computational graph completion problem. So how do you see the application of this? Because it seems quite general.
Yeah.
So I don't know how easy it is to employ very domain-specific knowledge. So for example, with the talk that Andrew gave you for, which was focused on fluid or continuum mechanics, how easy is it to incorporate that? And do you see any drawbacks because of the generality that it might not perform as well as more domain-specific methods?
I don't see specific drawbacks yet. So the power of kernel methods is that you can incorporate domain knowledge not only through the architecture of your graph, but also to the choice of the kernel. Let me give you an example of what I mean. So this is taking me to the Navier-Stokes equation. So example, Navier-Stokes equation, you know that the solution U is divergence-free.
Yeah.
You can encode that into the choice of kernels. So for instance, so if you can use a GP method to solve this Navier-Stokes equation, but you would like your kernel method to be such that the resulting numerical approximant preserves the divergence-free property of the solution. And the way you do that is that, so let me skip all these things. The way you do that is that you start with a given scalar kernel, and then you take the curl and the curl transpose of the curl of that scalar kernel, and you get a matrix-valued kernel that is going to lead to approximants that are going to automatically be incompressible, right?
Okay.
So here I'm encoding divergence-free property. You can in fact also encode scaling laws, like the Kolmogorov 41 scaling laws. The way you do it is that you write the kernel that you pick to represent or approximate your solution, you write it as a sum of kernels oscillating at different scales. So you essentially try to replicate the Richardson cascade. And then in this sum, you put some kind of power law. And if you choose the right power, you are going to essentially exactly replicate the Kolmogorov 41 scaling laws. And if you do that, you see that you get better accuracy by choosing the right kernel. So I didn't discuss at all the choice of kernel in all these methods, but the choice of kernel is extremely important if your problem is not just regular, but has some structure.
Okay, yeah. Thanks a lot.
Thank you.
Your slide claims that this generalizes to arbitrary nonlinear PDEs. But the introduction seems to suggest that it only applies to PDEs with strong solutions. What if you have weak solutions? Like you showed the Burger's equation.
Yes.
But it has viscosity. What if it's the inviscid Burger?
So, okay, so there are two things. You can have the right-hand side being singular. This is ongoing joint work with Andrew and Mathieu Darcy and Edo. So we're working on this. Your second question was?
The inviscid Burger equation.
So we don't know how to handle the shock well yet. The reason is because you need to choose a kernel that essentially can capture the shock. Yeah. So the limitation of the method is that you have to assume that the solution belongs to the RKHS space defined by the kernel key. So if you have a PDE that develops a shock, then you know that the solution will not be an element of the RKHS space defined by a mattern kernel or smooth kernel. So you lose that assumption. So you lose all guarantees.
Right. That's what.
Yeah.
Cool. Right.
Hi. As I understand it, Gaussian processes have a weakness in that they're pretty slow to compute when you have a lot of observations or a high-dimensional space. Does there come a point, or have you encountered a point at which it becomes intractable to compute?
So in high-dimensional space, yes, eventually once you exceed something like 6,000 points, and you're truly high-dimensional, then your workstation will not come back if you go beyond that. But if you're in a low-dimensional space, like space of dimension 2 and 3, we have implemented kernel methods with 1 million points, and we got machine precision accuracy in 10 seconds on a laptop using these sparse Zariski factorization algorithms.
That's really cool. Thank you.
You're welcome.
This is another question about scope and domain of applicability. In the little proof sketch that you showed towards the beginning of the slide, you made some geometric assumptions about the domain. My question is, I'm not very familiar, but are these purely technical and you would have to deliberately cook up some pathological examples for this not to be valid? Or is the geometry of the domains that you can solve these problems in practically restricted, and if so, what are those restrictions?
So the assumption that I made is that the domain is compact with Lipschitz boundary.
Lipschitz boundary is the...
Meaning that it is kind of a little bit smooth, right? Okay. It's a classical condition that you see you also see this kind of type of conditions for finite element methods. Traditional methods have this type of conditions. All these methods will essentially break down if you have a boundary that does not satisfy something called the interior cone condition. So if you use a star-shaped method, then this assumption breaks.
Like a star-shaped domain?
Star-shaped domain.
Thank you. Oh, okay. Thank you.
Okay. So we're breaking off the lunch posters, and let's just thank Houman again. Thank you.
Thank you.
6 talks on various applications from 5 faculty at Caltech and 1 who will be a sabbatical visitor next year. We're going to start with Tim Colonius, who's going to talk about his work in learning in computational fluid dynamics. Tim.
All right, great. Thank you very much, Andrew. Good afternoon, everyone. It's really a pleasure to be here. So we've heard a lot about fluid dynamics applications of machine learning already today. I think a simple message from my talk is an overwhelmingly positive one, which is that machine learning is finding interesting and useful applications in all corners of fluid dynamics, which really encompasses a broad range of different kinds of problems and different kinds of approaches to learning. Things I won't talk about today, but are very exciting, are feature extraction, looking at techniques like super resolution, solving complicated flow control problems, and finding simple or parsimonious models of complicated systems. But what I want to talk about today, mainly because it is something which I think resonates with the themes of this workshop, is predicting complex and turbulent flows. So computational fluid dynamics has been an approach that's been developed over decades now. So it's a mature set of modeling principles and algorithms. In general, we strive, of course, for fast, efficient, and scalable methods, but also ones that are flexible and robust so that they're applicable to a wide range of applications, both in terms of scientific inquiry and in terms of engineering practice. You'll find in the CFD community a lot of skeptics, a lot of people that look at numerical solutions and grill them to find, to make sure that they think that they're solving the equations right and they're solving the right equations. We have a lot of both physical and numerical understanding of artifacts of discretization of flow problems that help us understand how to design these algorithms. I'm not sure where the GIGO name, garbage in, garbage out, got originated, but it's a very common thing that you hear in computational fluid dynamics, trying to understand how good our solutions are. And also part of CFD is not just the Navier-Stokes equations. There are a broad range of different kinds of flow models that suit different kinds of situations and different budgets. And so there's already a wide array of human and machine learned models that are available within this framework. And yet we face serious limitations, and the big one is the time to solution. And I'll show you examples of turbulent flows where we don't have enough time to wait for solutions. But beyond that, there are other issues, uncertainty quantification, which we've heard a little bit about today. Even if we can solve one simulation, that doesn't help me know how good the answer to that one simulation is when there are stochastic or uncertain inputs particularly. And we also have to contend with discontinuities, which I'll talk about, and of course in the modeling array, dealing with the problems of creating good turbulence models. So within this computational fluid dynamics world, there's a huge scope for machine learning. I think it's this scope that is like partly daunting. There is space for making conservative approaches, for making little inroads on problems, and there's space for radically different approaches. And we've already seen mostly really the former today. But to give us a little context here, part of what makes us able to have this conversation in this auditorium about machine learning is the explosion of computational power, represented here with Moore's law. Transistors double every 2 years. So I've been lucky to have an academic career spanning 30 years of this plot. If we think about turbulence theory, it tells us that the range of scales in a turbulent flow is proportional to the Reynolds number. The Reynolds number is a non-dimensional parameter that tells us how fast things move in a flow compared to how fast molecules diffuse in a problem. And in typical engineering applications, this Reynolds number is a large number. And theory tells us that the range of turbulent scales in a flow scales like the Reynolds number to the 3/4 power. So when I multiply that by 3 spatial dimensions in time, I get a Reynolds number cube dependence, which means that I should expect that in order to do that the Reynolds number that I could achieve in a simulation should double every 6 years as opposed to every 2 years. And lo and behold, if I look at the history of turbulent simulation in the context of one simple flow, this is a turbulent channel flow, our simplest model of a turbulent boundary layer. The very first successful direct simulation of this using the Navier-Stokes equations occurred in 1987. And the Reynolds number was 180. And if you plot the subsequent developments all the way up till the present year, this was very recently published at a Reynolds number of, I think it's 10,000. You see that this follows this scaling precisely, which tells us that, first of all, we could have expected these developments even in 1987. And in fact, people did expect these developments. But really, more importantly, when we look at the data that's generated by these simulations, we see a problem, and a problem that's not just a problem of big data, but having the right kind of data. So in order to compute a turbulent channel flow at a modest Reynolds number of 10,000 costs a computational grid of 10 to the 11 points. So earlier today, I heard the number 6,000 raised as a large number, right? This is many, many orders of magnitude greater than that. And so that's big data, but it's not the right kind of big data necessarily for machine learning, because this is just one particular flow. There are thousands of different flows we might wish to model. And moreover, this flow is carefully arranged to live on a sort of turbulent attractor. There's kind of an underlying attractor to the dynamics, and the whole point of the simulation is to get the simulation to live on that attractor. And so the data that we would get from this simulation is really not that expressive of, for example, transients that I would need to know if I have a general purpose model that wants to seek this attractor from some arbitrary initial condition. So we don't necessarily have the ability to generate substantial amounts of different flow fields with different random initial conditions, different configurations, and so on. That ends up being a bottleneck. Okay, so within that context, I'll just give you a perspective of a flow modeler here. It's not very different from any other field in mechanics or really in computational science in general. So when we're solving a flow field, it's not just the Navier-Stokes equations we need to set up a specific flow of interest. We need a geometry, typically an immersed surface in a flow, and very importantly, we need boundary conditions. So boundary conditions are the thing that we know that gives us interesting and unique solutions to partial differential equations. For the Navier-Stokes equations, it's the only thing that separates the answer we want from the answer that the flow is zero, right? So boundary conditions are of tremendous importance, and then these get incorporated into a numerical method, which classically is one of the ones you've heard mentioned today, like finite difference, finite volume, finite element, spectral methods, and so on and so forth. And then finally, when we're dealing with turbulence or other stochastic phenomena, a part of our flow modeling is always inherently that we're going to need to be somehow seeding this flow with disturbances in order to get some kind of realistic realization of a process, which after all is incredibly sensitive to initial conditions, right? So much so that it's often more useful to take a stochastic view of a turbulent flow, even though we believe that given an accurate enough initial condition, we could deterministically evolve it. Okay, so that's classic. So what are we going to do with data here, right? So, obviously the most trivial thing that we can do with our data is validate our numerical simulations. And this is a critical thing, and especially in turbulence modeling, because turbulence data is hard to get in the lab, and it's nice to be able to use numerical simulations as a way to get additional data in order to discover things about turbulence. So once we validate that data, we can indeed harvest it and increase our data set. But more to the point of this audience, we want to use data to improve our simulation and or reduce its cost. And of course, this process has been going on for many decades in a human-learned fashion, and so we want to look for opportunities to do this process with machine learning. And I think the really tricky part here is to look at this overall problem and try to imagine where is the low-hanging fruit, where is the place where machine learning is going to make a big dent. And again, we've heard a lot today about the idea of kind of replacing this whole apparatus with a neural operator or other kind of technique, and that's fine. There's nothing wrong with that. It's kind of a radical approach. It's a paradigm shift. If it's successful, it will make a big difference. But what I want to highlight today are some opportunities to look into some of these little pieces and see if we can improve the pieces with machine learning. And I think I'll skip that box. This brings me to two little vignettes I'll just share with you quickly today. These have to do with an additional phenomenon, and I've heard this mentioned several times in the morning session, which is what happens when we have discontinuous solutions. So we're interested in my lab in a number of flows that involve shock waves and material surfaces. So materials between two fluids, materials between solids and fluids, and so on. And from a numerical grid point of view, those molecularly thin surfaces are best treated as discontinuities. So we want to be able to evolve discontinuities in the solutions of our PDEs. And two particular model problems that I'll tell you about. This is a shock droplet interaction. So this is a problem that we solve to try to understand how cavitation bubbles may damage materials, but the model problem is set up so that I have a bubble here, it gets hit with a shock wave and the bubble collapses. And as that bubble collapses, it undergoes an interesting dynamical phenomena where it creates a jet, and at the same time that the jet impinges on the distal wall and the bubble collapses, it generates a shock wave that impinges on the surface. So this is a relatively simple flow, but it's one that involves these thin interfaces. And I'll tell you about a little bit about our effort to try to improve the numerical methods that we use for those problems using machine learning. And then the second problem has to do with a problem where I can't possibly resolve all of the bubbles in a flow. Here I'm interested in how an array of bubbles are responding to an ultrasound pulse. This is a problem that has a medical application, but what we have the setup here is basically I have a cloud of bubbles, and I can't hope to resolve all of those bubbles using a numerical simulation. The grid would just be prohibitive for that. So I'll tell you about using machine learning to try to learn an improved closure model for those bubbles. Whoops. So let me start with the trying to improve shock and interface capturing. I need to do a little bit of background here, which probably will not be very unfamiliar to many of you. So traditional finite difference methods construct derivatives by taking a sum of adjacent values and a set of fixed coefficients for those values. And then we can have different schemes by choosing these coefficients in different ways. The problem is when I expose this kind of formula to a discontinuous solution, I generate oscillations, a kind of Gibbs phenomena, if you will. And those oscillations in nonlinear simulations lead to instabilities, and eventually these schemes become useless when faced with discontinuous solutions. And so over many years, people have developed what are called shock capturing numerical methods. And a central aspect of those methods is that the coefficients are made to be nonlinear. They're made to be functions of the solution itself. And a particular version of this is called the WENO scheme, weighted essentially non-oscillatory scheme, that tries to make the dependence on the coefficients by looking at what would happen if I took different stencils across a discontinuity and computed differences on these different stencils, and then compare the resulting smoothness of the function computed in those different ways. And by taking some linear combination of those particular guesses, depending on how smooth they are, weighting the smoother ones more, weighting the less smooth ones less, I come up with an approximation. And this naturally does a kind of what is called an upwind bias to the numerics. And that turns out to be what's favorable for evolving shock waves, because an upwind bias of the numerics turns out to dissipate or diffuse the solution a little bit. So it allows us to tolerate some amount of wiggles and so on without the code exploding into instability. Okay, so these nonlinear functions are human-made things. They depend on having intuitions about what the structure of the problem is. So we thought it would be interesting to say, what if we just pick these coefficients using a neural network rather than using the schemes that have been developed? Well, we formulated this in a particular way, though, so that we try to use a very good scheme. This is the WENO 5JS scheme, Zhang and Xu, which is already a very good WENO scheme. And so we're going to start with that scheme, and then we're going to try to perturb the coefficients. And we're going to perturb the coefficients with this neural network. The only thing that's, it's going to be a really shallow standard neural network here, nothing very complicated. The only trick that we do is that once we perturb all the coefficients at the end, we make an affine transformation of the output coefficients to ensure that the coefficients sum to 0, which would give us a first-order accurate finite difference method. So how do we train this neural network? Well, this is very, very simple. We say this differencing strategy is going to have to be able to difference different kinds of discontinuous functions. So we just generate a bunch of functions, sines, cosines, hyperbolic tangents, sine waves. We put them in a big database. And I should mention, we're actually training a finite volume scheme, which is roughly analogous to the finite difference schemes I've told you about. But in this case, we're actually integrating the solutions over cells rather than differencing them. But in this, so basically all we have to do to train our method is pick a bunch of functions that we know the integrals of, right? So that's quite easy, generate this. And then we train the network by basically seeing whether or not the new coefficients accurately integrate these different functions in very standard ways. And we were really shocked when we got the first result of this, which is that we got a very substantial improvement of the neural network over the state-of-the-art scheme here, the Wino5JS, for solving this very simple advection equation with a discontinuous set of initial conditions. So this is the error from our neural network versus runtime of the complete model. And the different dots are many different initial conditions on many grids. So you see that the Wino NN here outperforms the state-of-the-art method by almost an order of magnitude in all cases. And this is a very fair comparison because we're actually looking at the runtime of the overall method, right? Not just the accuracy of the solution. And one of the properties that really intrigued us when we started to look in at what the neural network was doing was that if we took a discontinuous initial condition like this step function, yes, like the kind of standard methods, it would smear that out. But you notice that over time, this is basically just a unit step periodically advecting in a domain. So the solution returns to this same picture every period. And I'm showing you the solution at different periods here. What you see on the right is that the solution continues to diffuse out over time. And this is an analog of what happens in real flows that have material surfaces. Those material surfaces tend to spread out over time, and that becomes very non-physical. So we want those interfaces to remain sharp, and you see that the Wino NN has this kind of almost miraculous property of keeping that interface exactly sharp. So we were sort of intrigued by that feature. So we went on to say, well, maybe this is a good approach. Let's expose it to a slightly more complicated set of equations. So we upped things to the Euler equations now, nonlinear first-order system of hyperbolic partial differential equations. This is a standard kind of test problem, and my animation isn't working well here, but sorry, the equations are buried. This is a Shu-Auger model problem. It's a shock wave interacting with some density fluctuations. It's kind of a model for a shock turbulent kind of interaction. And it generates a very oscillatory solution near the shock wave. These are physical oscillations, not numerical ones. So if I zoom into this region, you can see the performance here now of our Wino NN on different resolutions, and things aren't nearly as good as in that 1D advection equation. In fact, the convergence here is kind of spotty, right? Things look very good at 80 and 180, we're still beating Wino JS, but suddenly at 320, the situation reverses and Wino JS is much better. By the time we get to a very high resolution, they're both roughly the same solution. So we somehow in that process lost some of the goodness of this simple neural network. So, well, of course, this network was very simple. It knew nothing about the actual solutions of these PDEs. So our next step was to say, okay, let's make this real now, and let's sort of take this network that we've established that is good at integrating these kinds of discontinuous functions, and let's expose it to real solution data. So what we originally wanted to do was to test this in situ in a big numerical solver for the full compressible Navier-Stokes equations. My student, Ben Stevens, whose work I'm showing you, tried that very earnestly for a number of months and unfortunately was unable to get that to work. The best he could do was to be able to train models in PyTorch. So this is, I think, a problem that is kind of universal in the AI meets science community, which is we have a lot of legacy code. We'd like to be able to train neural networks using that legacy code, and that turns out to be a very difficult thing to do. So what Ben did was to reprogram at least the 2D Euler equations in PyTorch. And then we took this existing network and we used transfer learning to try to improve the network by training it on actual solutions to problems. And that was rather successful in the sense that we were able to have the transfer learning always come up with solutions, come up with models that were better than the baseline case, so better than the state-of-the-art scheme. This is the error ratio, 1 being the JS scheme, and these are probability distributions from many thousand different random initial conditions that weren't seen in the training, and so on. So this was, reasonably successful, but it's a big leap to put this into our code because, first of all, we can't really make any kind of runtime comparisons because all of this is now running in PyTorch. So we really need to look at what happens when we do this in situ in our big code to know whether this actually buys itself into a big numerical simulation. So I didn't time things well, and I am running out of time. So I had a second vignette about model closure. The machine learning we did here is really very, very standard. What is interesting, I think, is a kind of a different application area for doing machine learning. So we were trying to learn closures for collections of bubbles or particles or droplets in a numerical simulation, and we were doing so by modifying an existing paradigm for doing that, which is called a method of moments, and in particular, the quadrature-based moment methods, which are a very highly effective numerical technique for dealing with that, but they suffer from a serious problem that as I go to higher and higher dimension in the probability space with those models, they rapidly become not only very expensive, but also unstable. And what I would have showed you with time is that we can train a neural network to perturb the weights and the abscissas of this moment method in the probability space in order that we end up getting a much more accurate representation, a much more accurate evolution of the PDF. This is just a pretty plot of the probability of finding some bubbles with a particular radius and a particular radial velocity at a moment in time. And these bubbles are oscillating. So you see that in this RR dot space, they're following a kind of a trajectory here. Initially, this is a Gaussian blur of our bubbles. And then you see as the bubbles evolve, the statistics are anything but Gaussian. The probability function is anything but Gaussian. It really gets highly deformed as the bubbles collapse. And the speed as it's moving around phase space is very complicated and so on. The red points are the standard QBMM method, and the blue points are a recurrent neural network in this case that's been trained to try to match statistics from doing a Monte Carlo approach to the same problem. So both of these are really simple applications of machine learning, but they make important contributions in these different parts of this overall idea of flow modeling. So I guess my message is that there's a lot of space for a lot of opportunities in fluid dynamics modeling really at every level. And it's very exciting to think of whole new paradigms to replace the entire simulation technology, but these simulations are the workhorse of many scientific and engineering tools. They have a lot of thought and a lot of creative energy that's been put into making them. So I think it's also a nice idea to look at where can machine learning intervene at more microscopic levels in this process in order to get us better simulation code. So I apologize for going over, and thank you all for listening.
Thank you, Tim. We do want to keep the time, so if Kaushik, if you could set up, and we'll look at questions after all three speakers. I think you're going to have to give your mic.
No.
Oh, you each have one. Okay.
Yeah.
Oh, that's clever.
There we go. What's going on here? Find my presentation here.
Okay, so next speaker is Kaushik, who's going to talk about supervised learning and multi-scale model of materials.
Thanks, Andrew. It's a great pleasure to be here. And I want to tell you a little bit more about the kinds of problems that Andrew talked about this morning, and in particular applications in material science. I'll start by kind of stepping back and making the point that material science and materials physics is an essentially data-driven endeavor. So there are many, many opportunities for using machine learning in these kinds of problems. The first point I'd like to make is the world of known materials is just a speck in the universe of possible materials. And you can do a little back-of-the-envelope calculation. A millimeter cube of material has roughly 10 to the 12 atoms. We have about 40 common elements, so you have 40 to the power 10 to the 12 potential materials. We don't know anywhere close to those, right? So there's a lot of material to be discovered, and this is very much a data-driven endeavor, and machine learning is actually having a real impact in this arena. I won't talk about it, but I thought I'll kind of make that point. The second point I'd like to make, and this is really why the first point works, is that very small changes in composition, trace elements, trace small volumes of defects have a profound effect on the properties of materials. In electronics, we talk about parts per million, parts per billion. If you look at classical alloys, the specifications are done with very, very small trace amounts, right? So if you'd like to understand that, you really have to understand a very, very large amount. And what is made worse here is that history of how the material was made, how the material was processed, has also an enormous effect on these things. The third point is that it's very hard to observe details of materials in a very natural way. So the way we observe it is always indirect. Even if you think about simply understanding the structure of a crystalline solid, we actually look at diffraction peaks through X-rays and then try to invert it to get it. It works well when you have simple crystal structures, but when you get to larger, complicated structures, it becomes very, very difficult. And as experimental techniques advance, this kind of indirect inverse problem becomes harder. Again, another area for trying to understand, use some of the emerging tools. Finally, this is the part I'll talk about, is that the reasons why defects have a very profound effect and that you have a very large class of potential materials is that the behavior observed, the properties we observe, is really a distillation of a large amount of chemistry and physics which operates on multiple time and length scales, right? So the way we think about materials and kind of when you're trying to think about models, modeling and properties, is you build a cascade of models starting from kind of density functional theory, which is the computable version of Schrödinger's equation in this context. Then you go through the atomistics, then individual defects, and then at some point you try to understand your material properties, right? And over the last 3-4 decades, there's been a paradigm which is called multi-scale modeling of materials, which is built up. You say you're going to build models at these different scales, and you make the assertion, the statement of faith, that at any time only two scales talk to each other. So if you're at some scale here, that regulates what goes on in the lower scale, and then you filter what is happening there and use that and the information above, right? And that's how you can connect all these scales up. But by and large, while we have had this paradigm, the way we have looked at this paradigm is very much in the context of modeling at individual scales. The communication between scales has been relatively weak. And what I believe is that machine learning and operator learning provides a method to overcome the barrier of talking between the scales. Okay? Good. So I'll talk about two examples, one at the very top, where I'm really looking at a continuum, two continuum scales, and then I'll talk about an example involving density functional theory. And I'll try to make two different points with these examples. So let's look at the first example, the one at the, okay, so one here. So I'm interested in dynamic properties of materials. This is a canonical experiment called the Taylor impact. So if I want to model this, I have some kind of the usual laws of physics that we know about, but then I have to do something to specify the material properties. You can call this the constitutive relation, you can call it the material properties, you can call it the closure relations. And of course, traditionally, we do this empirically. We do some experiments, try to kind of build some empirical models. But in the context of a multi-scale modeling of materials, I can think of these, say that if I look at any point here, It has some complex structure, and in the case of metals, which I'll talk about, it is made out of a very large number of crystals which are together. Each of these colors represent a different the same crystal, but with different orientation. And what you're seeing at this material point is the kind of collective behavior of this ensemble, right? And each of these crystals, of course, deforms, undergoes plastic deformation in complex ways depending on the crystal structure. And I'll talk, and that's what I try to represent here. So the theory of homogenization gives you a kind of mathematical framework to work on this. It says you write down your equations here at this scale, you write down the equations at this scale. So if you take any point here at any instance of time t, this provides you the average deformation that this ensemble is going through. You solve the problem here with the fine details. You average it, and that tells you what the stress at that point is, right? So regulates the behavior of the small scale, and you average the behavior of the small scale, and you upscale it, right? So that's the kind of paradigm that we work with in a two-scale setting. And the question is, how do you implement it? One is you can say, let me try to do this brute force. So at each point, at each instance of time, I have to do a whole simulation here. So you have an order of a few thousand elements, probably more here. This is probably of the order of 10 to the 6, 10 to the 7 in terms of resolution. And you have to do this at every instance. It's a great idea. And there are people who have done it, but they've done it to say that they have done it. It's not really a practical approach. So the practical approach has been really to build an empirical model, but use these simulations to fit the parameters. But the fidelity of that only depends on the fidelity of the empirical model you've built. And so the question is, can we generate data by solving this problem and use this to train a surrogate which has a higher fidelity? So I'm going to show you, we did this in the case of magnesium alloys, which is of interest because magnesium is the lightest metal. It has a density of about 1.5, but it can have strength. So it's about half the density of aluminum, but it can have a strength as high as that of aluminum. Unfortunately, unlike aluminum, it can fail catastrophically very quickly. And part of the reason why all of this happens is because it has a very anisotropic crystal structure, and therefore there are many different deformation modes which interact in complicated ways. So if I'm trying to understand this kind of behavior, I really have to incorporate this information. The kind of empirical models we have are not very good representations of this. So that's why we tried to do this in this example. So coming back to the picture I had here, this is what I'm trying to implement. So I want to replace this with a surrogate model. So in other words, what I try to do is to seek, this is my black box, which I'm going to use to generate my data. I'm given some history of some deformation gradient up till time t, and this black box gives me the stress at that time t. And I want to use this data to try to learn what this black box is. And we do so by trying to introduce a parameterized approximation, and I'll tell you a little bit of what we do, right? So that's the task that we're interested in. And we want to do this in a time-continuous formulation because we want it to be a resolution independent. We might want to train it at one time resolution and use it at a different time resolution. Also, we want to learn the physics, not the particular discretization. We want this map to be causal, the behavior at time t only to depend on the history before, and we want it to be efficient so that I can use it in the higher scale simulations. So this is the architecture we ended up with, and it really drew from what we have known in continuum mechanics over a long period of time. The plastic deformation depends on the history of the deformation. The state of stress now depends on the history of prior deformation. And we have found that trying to represent history using state variables or internal variables has been a very efficient way of doing this. We also know that the history kind of fades as we go time. So this turns out to be a fairly well-established, we have a lot of experience with this kind of representation. So we said, OK, let's try to look for a neural operator which has this particular representation. The stress at any time t depends on the deformation at that time t and some state variables there. And the state variables are overdamped or evolve according to a first order in time equation. So here, f and g are going to be unknown approximations. That's what we'd like to learn. And so in this work, we took them to be feed-forward neural networks. And part of the training with the data is not only to learn f and g, but also to learn what the state variables are. So we don't assume them a priori. That's part of what we try to learn using the data. OK. Want to make a point here that you'll see that this architecture is different from the kind of LSTM and GRU and other RNN architectures that people use in natural language learning. And that's because simply the way history gets reflected in the behavior is quite different in these. And that's the physics that we tried to incorporate with this particular architecture. Okay. Try to do, and you interpret it in a discrete way where the time is actually a parameter. So then the question is, how do I sample this? So in other words, how do I generate my training samples? Which means how do I evaluate this map and how many state variables? Because as I said, that's part of the learning process. So what we did was we said, in the applications we are interested in, we know that the stress kind of fluctuates, goes up and down. But generally, with time, it is smooth. So what we did was we took some fixed interval of time, we divided it into arbitrary subintervals, and then each component of the imposed deformation goes up and down with this way. So we found that that has been, it's completely empirical. I would love to know more about how to sample, but we have found that empirically this turns out to be a good way of sampling, at least for the kinds of things that we want to do. OK, so we did this. We solved these kinds of problems. We generated data. And then we started trying to train the neural operator. In the interest of time, I'll only show you one example. And what the way we did this was we assumed that there were no state variables. This is the kind of test error we get. You assume that there's one state variable. You get this is the error. And we find that the error decreases with the number of state variables, but at some point it saturates. And there was in this example, there's a sharp elbow. In many examples we have looked at, we find sharp elbows. But there are examples where it's rounded, but still you find that very much there is this kind of training error gives you an indication of how many state variables you'll need to try and represent the data that you have. Just to make a point, these errors are integrated over time. And if I try to train a classical model using the same data, it turns out to be, it does really, really worse on the data. Okay. Having trained this RNO, in this case with 5 state variables, what we did was we incorporated it into a favorite widely used kind of finite element package. And we went out and solved many different problems of this kind. We were interested in a bunch of impact problems, and those are the kinds of problems that we tried to solve. OK, so 2 points to make. One is, I said, it's important that we have resolution independence, and I'll demonstrate it in 2 ways. We took two different time, did it in 2 ways. One is by taking different time resolutions in the macroscopic simulation. And you see that the results don't change. We trace this back to actually integration errors rather than to the RNO error. And the other way was what Andrew showed this morning, in which case, actually, this is the example. You train at a particular resolution. You change the resolution, and the orange curve is the curve of the one which I showed. This is a different architecture, and you see that this architecture doesn't represent the physics correctly, and hence trains it at the resolution you train it, but has a poor resolution elsewhere. So this is the cost. If I did my macroscopic simulations by an empirical law, this is the blue line tells you the cost. This is the cost of doing it with the RNO that I showed you. So it's really incremental. So really you're doing a simulation at the cost of empirical models, but with the fidelity of a lower scale model. So this really becomes a very effective way. There's a one-time cost of generating the data and training, but that turns out to be much smaller than the estimated cost of doing this a single concurrent multi-scale problem. So this is a very, very efficient way of doing this. There are a large number of open questions, but that's the kinds of things that we are thinking about. If I can impose on you, Andrew, I'll take another minute or two. And OK, so we're now also trying to study problems on groundwater, but I wanted to show you an example here. And it's a different problem, and I wanted to make a different statement. So this work was motivated by trying to study dislocations, which are one of the kind of main defects that you find in solids when you're interested in mechanical properties. What's intriguing about dislocations is that if you think about it, you can very quickly convince yourself that this is a defect which actually has a very strong coupling across all states. I can change the macroscopic state of stress, and that affects the quantum mechanics of the core. So there's a direct connection between the macroscopic deformations and chemistry. And that's part of the reason why in materials, very small trace elements have a huge, profound effect. It's because of defects of this nature. So over the years with Michael Ortiz and a group of students and postdocs, we have developed this approach to try and solve density functional problems on very large domains. So you have to do the high fidelity theories, density functional theory, but on very large domains. And we have an approach which leads to a sublinear scaling. And the way we do this is by kind of playing around with resolutions. But one of the things we found is that surprising the main computational cost comes with the repeated solution of small problems. So we wanted to explore whether we could use this kind of operator learning to learn the solution so that I don't have to repeatedly solve this. And here is an example. So you take a unit cell, you deform it, and you want to calculate the electronic states and the energy. And what is very important here is that you have a very, very high accuracy. When you're looking at dislocations and structures like this, when you're studying materials with density functional theories, you're often in this kind of unfortunate situation of trying to compare small differences between two large numbers. So you have to have a very high accuracy. And the question was, can we get this high accuracy using some kind of machine learning? Okay. So we used an architecture very similar to the architectures that Anima talked about. So we take so you distort the unit cell by some matrix F, and you calculate the electronic fields and the energy. And that's the number we are interested in. Okay? So if I did this, here's the kind of accuracy that I get. If I just look at the energy that by direct learning, this by itself is not bad, but in the long term, it's bad. But then what we did was we used the learned solutions as a preconditioner in the density functional theory. You solve this by iteration, so you do one iteration, and you get a dramatic improvement in this number. And this is far beyond what we actually need. So this shows you that even in places where you need high accuracy, you can use machine learned solutions as a preconditioner or as an initial guess in an iterative scheme. And with very little cost, you get a very, very high degree of accuracy. So those are the two examples I wanted to show. Sorry that I've gone long. But really the point is that When you're studying materials, you really are often repeatedly solving a problem. You're changing some boundary conditions and solving the problem. And there's a real opportunity of trying to use this approach to learn the operator and then use this as a closure relation. And then also, you are optimistic that you learn some physics that you didn't know before. So with that, I'll stop, and I'll actually put up the names of my collaborators, Andrew, and of course, Burigede, who was a postdoc, Margaret, who's sitting here, Erik, I don't know whether you're around, no, he's in, and this was in the larger context of neural operators with Anima and her colleague. And the DFT work was done by Ying Shi, who's also here. There we go. Thanks.
I think in the interest of time, we'll move on, but thank you.
All right.
Okay, so I'll wait till you share. Final speaker in this mini session is Tapio, who's going to talk about AI-accelerated climate science and prediction.
I'll continue on the theme of multi-scale problems, and if you think about the biggest multi-scale problem you can fit on Earth, this is probably it, almost by definition. So I'm going to talk about climate prediction. Why we do it, I think, is relatively obvious. Earth has warmed something like 1.2 degrees since the Industrial Revolution. It continues to warm. Climate is changing, and we don't know very accurately how it is changing. We know Earth is warming, but in detail, we don't quite have the information we need to plan proactively. We know we'll most likely have to live in a world that will be, on average, 2 degrees warmer than the world used to be in the 19th century. And on average, 2 degrees warmer means it's a good bit more than 2 degrees warmer in high latitudes, for example, where the warming can be 4 or 5 degrees centigrade or so. And if you ask current climate models where we are going, already just in terms of the global mean temperature, which should be one of the more easy metrics to predict, you get widely divergent answers. Here's one example from the recent IPCC report. If you just focus on a line that shows 2 degrees warming above pre-industrial times, there are all sorts of little lines, each one of them being a climate model in 2 colors. One color is a higher emission scenario, one is a lower emission scenario. So if you focus on a 2-degree line, this graph gives you the answer, when will this 2-degree warming threshold be crossed? And you get very different answers from different models. In some models, we already crossed 2 degrees warming. Well, that's obviously wrong. In some other models, this 2 degrees warming won't be crossed before 2080 or so. And in between lies a range of scenarios of which we don't know which of any of them is right, and makes planning, proactive adaptation to climate change quite difficult. The fundamental reason that these predictions are uncertain is that the climate system is so multi-scale. It's just the same kind of things that Tim talked about, that Kaushik talked about. If you take atmospheric turbulence alone, it has scales from a planetary radius, 6,300 kilometers, down to a millimeter scale where energy dissipates. It's a Kolmogorov scale. And that's just the motion in the atmosphere. So that's 10 to the 28 spatial degrees of freedom, just in the motion of the atmosphere. In addition, you need to know what's going on inside the cloud, how cloud droplets form, ice crystals form. They're optically very important, regulating Earth energy balance, regulating how much sunlight is reflected, how large the greenhouse effect is. So these are scales of micrometers and nanometers. So if you would say we have to go to micrometer scales, you end up with 10 to the 40 degrees of freedom just in space. And in reality, you have to go to yet smaller scales. There's the quantum mechanics of radiation interacting with everything. So it's just a vast multi-scale problem that cannot be solved with brute force computing alone. So what a climate model gives you is variables like humidity, temperature, winds, and the like on a computational mesh, which typically in a climate model right now has a size of 100 kilometers in the horizontal. 10 kilometers is becoming routinely feasible. 1 kilometer is feasible for short simulations, but there is no scale break anywhere in the turbulence there, in the motions. It goes all the way to millimeter scales. So there isn't any special number that 10 kilometer is much, much better than 20 or 1 better than 10. What we have to do is bridge the scales between what we need to know, say droplet scale physics, that gives us large-scale optical properties like the albedo of a cloud, with bridge from these small scales, micro nanometers, to the scales we can actually resolve, which is, say, 10 kilometers or so. Computing alone is not going to do it, and just by counting degrees of freedom, we have a lot of data about Earth, something like 50 terabytes per day that we receive. That's great, but nowhere near enough to learn all these unresolved scales from data alone. So we are in an environment that's extremely multi-scale, and ironically, data are sparse, in that the degrees of freedom that we need to constrain far exceeds the degrees of freedom in the data. Yet, it is the golden age of Earth observations. We have, for the first time, for example, data on global cloud cover, 3D data on global cloud cover. This is a composite of various instruments, cloud-based, space-based radar and LiDAR, giving an image of a cloud. We have data about the Earth's biosphere, about the land surface, and the like. That's truly spectacular. We also have data that we can generate computationally, much in the way that Kaushik and Tim talked about. In this case, here's some example of a large eddy simulation of clouds. These are Caribbean clouds. Blue is rain, gray is a cloud. The surface, the color indicate buoyancy, effectively temperature. And these simulations are good in the sense that we can validate them with aircraft data, and we know that the numerics, for example, is robustly resolved. Microphysical processes controlling precipitation and the like are still parameterized here and are not robustly resolved. So the key question is, how do you use the data we have, computationally generated, and the observations we have to learn about all these small-scale processes that we have no way of resolving in the global climate model, down to micrometer scales. And now in climate, we have the additional challenge that we have to predict something that none of us have seen. We don't have data for the future, so we cannot learn a lot of what we want to know directly from data. We have a special requirement here that whatever we do is generalizable out of sample. That's true for other problems as well. But here, we don't have an easy way of validating what we do. The information we provide, we want to be used for engineering applications, perhaps for policy purposes, which means people need to be able to trust what we do. And I think the only way to achieve trust in something that cannot be empirically easily validated is that the model is interpretable, that you can tell a physical story of what the model is doing. And for practical applications, engineering applications, like how big a stormwater management system Pasadena should build, we need uncertainty quantification as well, not just a point estimate of what the future climate might be. And I think it's absolutely critical to meet these three requirements. And it creates challenges for using AI broadly understood in the climate context, although the challenges are quite similar in other domains of computational science, like the ones that Kaushik and Tim talked about. If you would want to reduce the success of deep learning to one keyword, it would be overparameterization. It gives you expressive models. The methods become very data hungry. But that same overparameterization makes generalizability, interpretability, uncertainty quantification challenging. And if you want to reduce the success of reductionist science to one keyword, I would say it's parametric sparsity. Take Newton's law of universal gravitation. It's one parameter in the law. And with that law, you can describe how apples fall from trees, how planets orbit stars, how comets orbit, and the like. It's extremely generalizable, interpretable, and certainty quantification is easy. Now, it would be ideal to have something like Newton's law for the macroscopic dynamics of the climate system, clouds and plants and the like. And now we don't have that, and there's probably no hope of getting that from first principles. So the challenge is here to use the best of both worlds, expressive methods from expressive AI methods with what made reductionist science successful over the last 400 years. So CLIMA is the Climate Modeling Alliance. It's a group of scientists, including Andrew, a number of people at MIT, at Caltech, at the Jet Propulsion Laboratory. And what we're doing is build a new climate model that at its core is a physical, chemical, biological model, but it uses AI methods in a judicious way where reductionism alone doesn't get you to success. Our approach is a hybrid approach, hybrid physics or biology, chemistry, AI approach, where we advance theory as far as you can go. You harness diverse data, and diverse data means data that are noisy, spatially incomplete, heterogeneous in various ways, Earth observations from space, from the ground, computationally generated data, and you leverage the computing power we have to the degree that's possible. For example, exploiting GPUs to enable many distributed high-resolution simulations. Andrew talked about some of the mathematics of what we do there earlier in the morning. Let me just give you a sketch and then a concrete example of how we use it. So in climate, what matters is to predict statistics of the system. You want to know the probability of extreme rainfall occurring, not necessarily whether there is rain on February 10th, 20 years from now. That's not predictable. But you can say something about the statistics of the system. What that suggests is to focus the learning from data on statistics of the system, because that's what we want to predict. It has ancillary benefits. So the statistics means here things accumulated in time, for example, perhaps in space. It overcomes an often cited mismatch in resolution between observations and simulations, because statistics tend to be smooth in space and in time. Statistics can include a number of things that we know to be relevant for climate predictions, like covariances between temperature and cloud cover are informative about the climate response of the system. What it forces you to do, though, is treat machine learning as an inverse problem rather than a supervised learning. And I'll say more about how we do this. And on the downside of the approach is that it's extremely expensive computationally, because every evaluation of a loss function means accumulation of statistics over a season, over years, and climate models are expensive to run, so that becomes an expensive operation to do. The statistics I'm talking about here is just one example. This is sea ice cover in the Arctic. It's a seasonal cycle, January, February, March through December, over the last 30 years averaged, and the colors are different climate models. And the black line is observations. And the arrows on the black line show you the approximate change in sea ice cover you'd expect over the next 30 years or so. And the key thing you see is that climate models have large biases in a key metric, sea ice cover, up to 50%, almost a factor of 2, have large variations in the amplitude of the seasonal cycle relative to observations. So here is one observed metric where climate models do poorly, and you can use it to minimize the mismatch between what climate models do and what's observed. So that's one statistic you could use to learn about processes in climate model that are responsible for this mismatch. Interestingly here, there seems to be a correlation between how well climate models do in simulating the statistics of the system and how large their sensitivity to human perturbations is. The color of the lines corresponds to their climate sensitivity, from lighter color to less sensitive, to red to more sensitive, which is suggesting that if you do well at simulating the seasonal cycle, you will have a better chance at also getting better predictions of the climate system. Andrew briefly talked in the morning about how to use ensemble Kalman methods for various learning tasks, and I won't belabor the point, just to say what we are doing and what is to come in the next few slides is use ensemble Kalman methods to learn about parameters, to treat the learning as an inverse problem, and the parameters here can be standard scalar parameters in the model, they can be biases and weights in a neural network, it can be parameters in a Fourier neural operator, and the like. To do uncertainty quantification, we use emulators that we train on the ensemble Kalman inversion, and then sample from the emulators effectively and efficiently to get uncertainties, posterior densities on the parameters. So this is fairly abstract. Let me just give you one slightly more concrete example how that actually works, and let me focus on modeling clouds, because that's what we do in my group. What we do there, so the theory part is this. You take a grid box in a climate model, and we know the equations of motion governing clouds. It's Navier-Stokes equation, laws of thermodynamics, plus particle dynamics. And we just coarse grain these equations of motion. We conditionally average them. Conditionally averaging means we average separately over more coherent structure of the turbulent flows and over less coherent structure, more isotropic turbulence. And what comes out is an equation set that is exact, the way I'm writing it down here. So we don't need to go into in detail what the equations are, but these are conservation laws, so the top for mass, the bottom for some arbitrary scale or phi. The important part is the overbar represents an averaging operation. Because we average, we lose some information, And that lost information shows up on the right-hand side as closure terms, functions, that a priori we don't know. For example, epsilon and delta represent the mass exchange between more coherent parts of the fluid and the less coherent part. There are various other functions appearing on the right-hand side, and the problem is we don't a priori know what these functions are. Now, in fluid dynamics, that's a generic problem that we've had for 100 years. What people do is reduce these functions to functions of some non-dimensional groups, and then traditionally people go out in the field and measure what these functions are. Say, measure over Kansas wheat fields what these functions look like. Now what we can do is we can generate training data, for example, computationally, or use observations, and learn these functions in more expressive ways using, for example, neural networks, and what I'm going to show you next. So in the example that I'm showing you is we generated training data by doing high-resolution simulations of clouds in various parts of the Pacific in this case. Those sites were chosen because these are areas where current climate models do particularly poorly. And we drove high-resolution simulations in limited areas with output from a climate model, generated a few hundred of these runs, and then trained a neural network for these closure functions on the output. And here's just one example. Iteration is the iteration number in Kalman inversion that we use for this. Blue lines show a linear regression model for comparison. The reddish lines is a neural network, and the green line was a physics-inspired closure we had handmade over several years. And the point here is that this is the validation error. So we train on some set of simulations for the present climate, and this is the validation error on a much warmer climate. And the error is decreasing monotonically, which is very reassuring, meaning this is generalizing well to out of the distribution of the training. And what's even more reassuring is the neural network seems to be doing, albeit marginally, but it seems to be doing better than any of the other approaches. So it's a successful way of learning neural networks embedded deep within the physical model, not in a supervised learning approach, but in an approach where the data we have about the process we are learning here are fairly indirect. It's cloud cover data. What we're learning are processes inside clouds, involving turbulence inside clouds. We have done this with random feature models, Fourier neural operators, and the like, and the approach works quite generally. Here is what happens if you put this all together into a closure scheme for clouds. So this is something that climate models notoriously are bad at, is simulating stratocumulus cloud. And gray line is the cloud fraction at a particular site over the Pacific from a climate model. Blue is a high-resolution simulation, which is replicating observations well, and red is this reduced order model that we trained here. This red model is still containing complicated physics, but it's something like a factor 10 to the 8 faster than a direct simulation with a high-resolution disk. Here's the same kind of situation now with observed data and showing cloud liquid, red is observations. And the point is, in all of those cases, we are matching observations pretty much perfectly, and it generalizes well. So the next step for us is to do all of that in a global climate model. We have these reduced order models that we are testing in isolated settings. The key is to do this in a global model, and that's what we're at. So let me leave it at that. I think the key of what I was saying and how we use AI is very similar to the kinds of things that both Tim and Kaushik talked about, that it comes down to learning closure relations that represent what small scales do in a model that resolves larger scales explicitly, and training the models for these closure relations with data that are not necessarily directly informative about the closure relations. So that's a bit different from what Kaushik showed. So say the data I used here are data that are macroscopic data on cloud cover, from which I learned microscopic models inside a cloud model. I should have said the neural network data that I showed in the last few slides were from 2 students, Costa Christopoulos and Ignacio Lopez Gomez, and all of that is work of a large team in the CLIMA consortium. So thank you very much.
So I'd like to propose the other 2 speakers come up and we open the floor for questions for all 3 of the last talks. And if we could use the mic on the stand, then all 3 of them can answer. Thanks. So please, as you did this morning, come forward and ask lots of questions.
Hi, Tim. Can you unpack what the Wiener neural network is exactly learning?
It's learning it's learning the integrals of a bunch of a function space comprised of.
Tim, I think you have to go to the.
It's basically learning how to integrate the functions that I showed on the plot on the plots. We create a library of discontinuous function comprised of sines, cosines, things with steps, all kinds of different functions. And things weren't very sensitive to how we chose that library of functions. It just needs to learn how to integrate these discontinuities. And again, it's finding corrections to the Wiener scheme. So it starts with that as it's finding perturbations to those, already good coefficients. That's all it does. It's really very simple.
So it's learn.
So it's learning a correction, right?
Yes.
Okay. Can you unpack what is the input and the output?
The input are the Wiener.js coefficients, and the output are a new set of coefficients, the corrected set of coefficients.
Got it. Thank you.
Tim, in fact, I had a follow-on about the same topic. Could you talk about the relationship to Michael Brenner, who also learned different stencils, and talk about differences?
Yeah, the two projects are actually very similar, and they were kind of conceived around the same time. Michael Brenner's work, for those of you who may not know, was similar in that they were learning a kind of finite difference stencil, and they applied that to similar kinds of one-dimensional and I think now two-dimensional problems. Their interpretation is that they're learning, our results are also independent of resolution in the sense that we learn a scheme that can be applied at any resolution, but they had a more specific goal of coarse graining the solution. And in a sense, when you're dealing with discontinuities, you're doing that as well, but that was not our explicit goal, was coarse graining.
Further questions?
I have a question for Kaushik. You said you also learned the internal variables as part of your process, but I don't think you got to describe that. So how were the internal variables learned in the method that you showed us?
So so when you create your so you're doing two feed-forward networks. You have inputs which are using, so you're using the same architecture at each time. So you're taking the output from the previous time, putting it as input. And that is part of the training. So that map is part of the training. And so in the end, the value of that output becomes your internal variable.
I see. Okay.
So you have an extra input and an extra output, and that's part of the training, and that becomes your internal variable.
Okay, got it. Thanks.
Yeah. Mm-hmm.
Hi, yeah, I have also a question. At the end, you mentioned that you hope also to learn new physics behind it.
Yeah.
Could you maybe explain what you mean by new physics, or is it like you try to learn some conservation laws, or is it data you hope to learn from it?
Yeah. So the state variables are representing the history. So the state variables have information, is encapsulating the part of the information from all the lower scale, high dimensional objects, right? And we would love to know what information it is encoding. Because if I know that, then I can understand what aspects of the smaller scale model affect the larger scale. That's the physics I'm trying to learn, and that's important if you want to try and do the inverse problem.
Okay. Have you already experienced like learning something from this?
In some simple examples, yes, but that's really what we're trying to do.
Okay, thank you.
Any further questions? Okay.
So for Kaushik and Andrew, you did the recurrent neural operator approach, right? So you're taking in the history and going forward with that. I mean, alternatively, you could also do Fourier transform in the temporal domain as well and directly output. So did you, and we've done that method, right, in some of the other previous work. Did you compare the two approaches, or was there a reason to go with the RNO?
So we haven't done the Fourier neural operator, but you may have seen there was something called the PCA net there. And you know that the first attempt was to basically use that, right? I mean, we used a PCA net that is a local version of the Fourier neural operator to do this. We find, this is empirical, we don't complete. So I think one big difference is when you look at the whole interval, you're not building in causality into your architecture, right? Because the response over the entire time interval depends on the input over the entire time interval. You learn causality from the data,
right,
but it's not built in, right? So in some ways here you're putting in the causality, and the experience is that this then leads to a much more efficient training, so you need much less data to train, and it leads to smaller errors. What that reflects, we don't know.
Yeah.
And the second thing I would say is then when you're using it in a larger scale simulation, it turns out that an RNO, because it's somewhat incremental, makes it much more efficient in the coarser scale model than you doing the full interval.
Yeah, that makes sense.
So those are the two differences.
Yeah. Thank you.
It may be also worth mentioning that it's more interpretable, I think, to domain specialists.
Yeah, Andrew just mentioned that, and I agree that it may be more interpretable to domain specialists, because as I said, this architecture is very much inspired by the kind of models that we are familiar with and we use. Yeah, I think that's a good point.
Okay, I'd like to thank the three speakers again. Thank you. I propose that we restart at 3:30 rather than 3:20, so an 18-minute break.
Oops. Let's get it out.
Thank you for coming back to the last session, and we'll continue with the applications track, and Zach Ross will be the first speaker talking about applications in seismology.
Okay. All right, so yeah, I'm a seismologist, an earthquake seismologist, and I'm going to talk about some of our work on trying to speed up and improve various types of fundamental calculations that we do. So what I'd like to do, just to kind of motivate some of this, is that I put here a video for a large kind of realistic scale earthquake simulation. This is for a magnitude 7 earthquake that would occur on the Hayward Fault in Northern California. So this black line here that you see is basically the entire extent of that fault. And so this is a wave propagation simulation to be able to characterize, expected ground motions that you could use for various types of design criteria and things like that. So it's going to run here. And this is a pretty involved calculation. You're going to see that basically the earthquake nucleates right here and then starts to radiate waves as it propagates across this region. This was done on a national DOE supercomputer, and it took millions of hours to run this simulation over this entire region up to something like 5 hertz in temporal resolution. And so these calculations are extremely involved, and ultimately what happens is that when you're done with the whole thing, it's been computed for a single model of what the Earth structure might look like in the subsurface. So millions of hours to do one run like that. And that's because the standard types of solvers that we use, which are finite element or finite difference-based solvers, are not able to handle changing the models for the Earth structure and so forth. And so that's very important for us, not only from this type of forward perspective to be able to accelerate all of this stuff, because we'd like to run this for ensembles of models of Earth structure, but also from an inverse perspective to be able to solve for that as part of fitting to data and so forth to get better models for the future. So we've been working over the last few years on using these neural operators to do this. I think you've heard about this quite a bit today already. So basically, I'll just talk a little bit about it for our problem, which is that we have the elastodynamic wave equation. And so what we want to be able to do is directly map from some input model of the Earth's velocity structure directly into the wave field output. And going from forward to the solution will allow us to then also backpropagate through that and update these inputs as well if we want to do some kind of inverse problem. Using this type of neural operator framework allows us to do this very efficiently. It's because of the fact that these parameters are shared across different discretizations. And I think as you've probably seen here today, it's very successful in a wide range of PDE circumstances. So I won't go too much into that. But for our problem, what we're working on right now, we've basically been focusing mainly on 2D problems so far. And that's mainly because of memory limitations and so forth, because when we go to 3D, it really blows up. But basically, we have an architecture that we designed recently called a U-shaped neural operator, which maps from an input velocity function space into the output displacement field. And the architecture itself has a series of these layers where you progressively contract the size of the physical domain while upsizing the dimension of the codomain until you get down, and then you reverse that. And so it has the skip connections just like a standard U-type neural network, except this is designed to exploit kind of the natural structure of the function spaces. But then kind of the layers themselves are composed of these Fourier-type neural operators. So this has a lot better performance than the standard Fourier neural operator and has other memory benefits and things like this that are quite valuable to us. And so we have this set up. As far as the data goes, for the purpose of this, we're entirely interested in simulation. And so that means being able to learn, the operator from input like this to the output simulation. So this is not data driven as far as the learning problem goes. And so we have a 2D case here where we have a physical domain that's 10 by 10 kilometers, and it's on a 64 by 64 grid. And so we want to be able to input a source function that drives this that could be randomly located within the medium, and an arbitrary velocity structure. We set up the data set to learn from using entirely simulations. And so we have a generator for these velocity structures that are drawn from random fields. And these have a von Karman type correlation function, which is basically a power law type, which is something that we know the Earth typically exhibits. And so we're putting that in there as part of the training data set. And so we set this up on the solver, which is basically a finite difference solver at 64 by 64 resolution. And so we generate all of these waveforms that we're going to do are 4 seconds long, and they're 32 hertz. And so we basically just generate thousands of these simulations, and it's a fully supervised problem. We just use those to learn this operator that maps from this to this. And so here's an example of the performance and how this results in the output solution when you vary the size of the simulation data set. So we have different cases here for 5,000, 10,000, up to 20,000 simulations for training and validation. And so it's very clear that the performance improves a lot as you go up to 20,000 plus. Here's some examples of seismograms, which are just selected from an individual point in space and looking at the time function. And we can see as we increase that, we start to fit more of the complexities in the wave field, even though the direct and larger amplitude signals are learned pretty quickly by the operator. And so, depending on, I guess, your intended purpose, maybe a smaller number of these could be sufficient for you, but we're often very interested in modeling these very kind of nuanced signals in the scattered waves and so forth that show up. And so, as I mentioned before, we train this thing on random fields. So even though we're using random fields, those are not completely representative of what we see in the Earth. In particular, the random fields don't have discontinuities in them. And yet, as I'll show you in a second, the model still generalizes well to structures that are quite different, that do have strong discontinuities and so forth. And we attribute this mainly due to the fact that the random fields are a dense subset of L2 space, and so it's still able to basically find a close approximation to these types of structures and still generalize well. So the other thing that we want to be able to do with our testing is be able to run these solvers at a higher resolution or a different one in terms of meshing than we started with. And so this is not just simply interpolating the output, but putting in an input that has a spectrum out to higher frequency than what we initially started with. So being able to evaluate that operator at a finer resolution and still have it construct the right kind of solution. So, so here are some examples of some of these tests that we're doing. So here is what our velocity structure looks like, which is very far removed from a random field. It's basically a homogeneous background with this diagonal stripe through it that's constant velocity. And so the upper row here is the finite difference simulation, and the bottom row is this generalization. And it's doing overall quite well. We've also studied in detail kind of the time delays using cross correlations and looking at where the peak of it is and so forth, and we find overall that it's not really biased in terms of the phase or anything like this. And so it works quite well. That's for a sharp interface. We can also look at a velocity structure that's even more complicated with lots of different layers. This is actually one that is from the real Earth. And so it's not a synthetic example. And as the waves are traveling through the medium, they're being scattered across all of these different faults and so forth that are embedded within there and picking up all these small scale features quite reliably. And this third case is what I mentioned before, where we wanted to be able to super resolve the solution. So instead of the input being 64 by 64, it's now being input at 160 by 160, which is basically, I think, what we could fit on a single card for this purpose. And so we generate the random field at that resolution with the spectrum extended out there fully. And so you can see that it still is able to generalize this, so the operator is not dependent on any particular resolution or meshing, but it does seem that eventually it starts to degrade, but I think that that's probably more numerical stuff. But we haven't tested that extensively on quite how far you can really push this. But even for this case, kind of the time delays that we get from cross-correlation measurements are on the order of like one time step in the wave field solution. So it's still quite accurate, even for this much bigger mesh that goes in here. So these are all on the forward simulation side. We're also very interested in using this for inverse problems. And so having this model that's differentiable lets us set up the inverse problem very easily. And so here are some examples of using this to do basically what we call seismic tomography, where you have some velocity structure that you start with, and you have a set of sources. In this case here, these are earthquakes that are located below the surface at these different stars for this toy case. And we want to basically recover that. For this case here, we have basically measurements at all points within the physical domain. So it's co-located with the node points that go in. And so here's an example of what we get out with no regularization when we basically just take the data from these simulations. We use this as a starting model, so it's homogeneous. And we just iteratively update this with gradient descent until it converges. And then here, if we use some kind of regularization here, you can see what we get. So it's not completely exact, but it is quite close. It's within a few percent of this initial model here. And there's some kind of intrinsic smoothing that's also going on there besides the regularization that we're imposing that we're still thinking about a bit. But this is helping us do this quite a lot faster. And in particular, it's, for this case here, it's something like 60 times faster than what we're getting with the finite difference solver for this 2D problem. And so, and we think that we're going to have additional performance advantages or efficiency advantages when we go to 3D for this, because a lot of the structure in this we think is kind of, we don't need to just simply scale everything by 64. So, but that's something that we're still playing around with right now. And then here's just an example of a more realistic case where we don't have observations everywhere. We have them only on the surface here as shown, and basically what that results in is sensitivity only within a specific range that's enclosed by the paths that the waves take through the Earth to the surface, and so forth. So, so basically this is good for both forward and inverse modeling. And we've spent a lot of time validating all of this and testing different strategies for improving it and so forth. So yeah, so we're looking at right now something like 60 times faster full waveform modeling and inversion using these neural operators. And it's making things a lot easier for us because we can just set this up with PyTorch to do the inversions and so forth. And so, yeah, we're thinking a lot about how to make this efficient in 3D and scaled nicely, and working with some folks at the national labs to bring this to kind of the scale of Southern California next, to be able to do some of these large earthquake simulations that we're interested in. So, yeah, I'll stop there.
Similar to the previous session, we'll take the questions.
Sure.
Okay, looks like it's working. Can everyone hear me? I think so. All right, I'm Erik Winfree. I'm a professor of computer science, computation and neural systems, and bioengineering. And my interests sort of span the principles of computation, but mostly how those computations are embedded in molecular systems, possibly biological systems. So there we go. So I'm going to start with a quote from my father. This was when he was an undergraduate at Cornell. He wrote an essay on the scientist as a poet, which I find enjoyable. He said, "Examining the commonplace from a strange viewpoint is a valuable eye-opener, whether practiced by the poet who stands on his head, better to see the beauty of a sunset, or by the scientist trying to visualize a crystal lattice from the electron's point of view. The object in either case is to divest a phenomenon of its obscuring incrustation of familiarity. So DALL-E came up with its interpretation of that quote, turning things on their head. So turning things on their head actually is quite powerful in science and has a long tradition. One of my favorite examples is the theory of the steam engine. People were building steam engines quite a while ago, and we're trying to optimize them, get them to work better. And Carnot tried to understand the principles that were limiting the efficiency of the steam engine and came up with a number of principles involving heat, power, work, and energy. And he had distilled these down, and other people later distilled them down as essentially the foundations of thermodynamics. And although this was originally the theory of the steam engine, now, 200 years later, it's almost impossible to talk about chemistry, physics, biology without looking at the heat, the power, the entropy, the energy, and these basic concepts that were refined for talking about a particular machine. So for the past 100 years almost, depends on how you measure it, we've had a new important machine in civilization, the computer. And people have been developing the theory of the computer. And slowly, these ideas are trickling out, and their application for understanding other kinds of systems is becoming clearer. So whereas many people today have been looking at AI4Science from this point of view, there's some scientific object that we want to study. We look at it, we get some data, we analyze it using AI, networks, probabilistic modeling, whatever you want. And there the computer is looking at the science. If we turn on our heads, we can ask, that thing itself that we're looking at might itself be an information processing device. Can we think about the AI inside that thing? Can the principles that we've learned help us understand the organization of natural objects, particularly in biology? So why might that be interesting? So if you're a computer scientist, you probably look at everything as code in some sense or another, and that's actually a natural thing to do in biology. A biological organism has DNA that codes for its proteins, its enzymes, everything that's controlling its behavior at the chemical level. And single organisms can do remarkably complex things. And so if we are trying to develop a view of the cell as some kind of mathematical construct that encapsulates the principles that we're thinking about, those mathematical notions are going to have to embody somehow self-organizing principles, self-healing. They have to be autonomous, capable of dealing with stochastic environments, adaptive, creative. It's some kind of information-based chemistry, and where are the concepts going to come from that help us understand this kind of information processing in molecular systems. So the thesis relevant for today is that neural computation is the branch of the study of computation that is particularly insightful for looking at biological systems. Of course, it came from studying a biological system, the brain, and so it's not too surprising that it has many of these features of being good with probabilistic inference, associative memory, being able to design computation that sort of works in any direction rather than following a strict path, having learning, optimization. All of these things have sort of come out from the study of a biological computation, but those principles might be more general and might be able to tell us something about molecular scale information-based systems as well. Okay, so that's why, sort of the introduction to why I'm here. These connections have a fairly long history. It's not a novel concept. People have looked at connections between genetic regulatory networks and neural networks since the 1990s, or signal transduction cascades in biology, and even in the past few decades have started building chemical systems in the lab that operate as very small neural networks with 1, 2, 4, 100 neurons, but that's kind of the scale that people can engineer. So I think there's something special about engineering in exploring how these ideas connect. Because when you build systems rather than study an existing thing, you can look at the whole design space and you can really test out whether your ideas work or not. And people have built things. So when we're inspired by certain things in biology, like a dog or a wolf, you might be inspired to try to build a robot that can also run through a forest, can jump over logs, can find things and search things. And of course, we know that computation is necessary to embed in that system to make it work. So we might ask whether in the future it will someday not be science fiction anymore to imagine looking at and being inspired by cell-scaled biological systems and asking, can we build a completely artificial synthetic cell? And in fact, I'll go out on a limb and say that we'll probably be doing that within 50 years. So if we're going to build something like that, we want to ask, how do we program it? How do we design molecules that carry out the tasks? Instead of having a silicon computer inside a robot that we can program to recognize its environment and take the appropriate action, we need to make a molecular system, putting it inside our artificial cell that will recognize the environment and tell that cell what to do, where to go, how to hunt, whatever it needs to do. So now I'll tell you two stories very quickly about the kinds of experiments that we do in my lab to explore this kind of connection between neural networks and molecular systems. So the first one, which is currently a preprint, pattern recognition in the nucleation kinetics of non-equilibrium self-assembly. This was, let's go back. There we go. The idea of Arvind Murugan, who actually was an undergraduate at Caltech, now an assistant professor at the University of Chicago. And it was done in my lab by a graduate of my lab, Konstantin Evans, who developed a lot of the simulation code and did the experiments. So the idea here, well, I should say sort of what the large idea is. What we want is to have a system of molecules. They're going to be DNA molecules that we synthesize, completely artificial. There'll be hundreds of them, almost 1,000. And what we want is a system that can recognize patterns in those species. So if I have 100 molecules and I vary the concentration of each one, a pattern of concentrations it's sort of like an odor, right? You can smell a forest after the rain, or a garbage truck, or a rose. These are different concentrations of, different patterns of concentrations of often very similar or the same species, but just in different combinations. So recognizing this sort of pattern of concentrations is a natural task. We do it every day when we taste or smell. So I'll be showing a pattern of concentrations as an image. That's just the grayscale of different concentrations. Because this is a toy problem, we're not taking those concentrations from any applied problem. We just want to see whether a system where an image represents a pattern of concentrations of molecules, whether those molecules can recognize which pattern it is and make a decision based on it. And the decision they'll make is either self-assemble into a H shape, self-assemble into an A shape, or self-assemble into an M shape, where this is about a 100 nanometer size object. So 1/10 the size of a bacterium. So that's the goal. The kind of technology we use is DNA nanotechnology. So this allows us to design DNA molecules with arbitrary sequences where we can code particular sequences to be complementary to other sequences so that they form a double helix. And if we design many of these molecules with the right complementarity, they will self-assemble into very regular non-biological structures, such as this kind of two-dimensional lattice, or as is being shown here, a three-dimensional lattice. And this is a fairly reliable technology that allows one to design thousands of molecules that self-assemble into the target shapes. So what we're going to do is not just design a system where each molecule is a specific place in a large assembled structure, but actually the same set of molecules, these 917 molecules, can, depending upon luck of the draw, stick to each other in different orders and self-assemble into one of three possible shapes. But it's the same molecules, or at least overlapping subsets of molecules that assemble into the three shapes. So the system has to make a choice. When it assembles into H, it uses up the molecules and can't assemble into A and M in a given instance. But if you have a whole test tube, you can get some H's, some A's, some M's. This is experimental results on this system, 50 nanometer scale bar here, where at the same concentrations of everything, you get H's, A's, and M's, as well as incomplete structures. The way kind of experiment works is we have a plate of tubes, one DNA molecule in each. We mix them in a various ratio. In this experiment, the ratio was 1 to 1 to 1. We put it in a test tube. We heat it up, cool it down. And after we've cooled it down, we look at it on an atomic force microscope and see what we've got. So the interesting thing about this multifarious assembly is that the logical connection of the components is analogous to a kind of neural network that's actually been studied in biology, hippocampal place cells, where if you put the pieces together in a certain order, they have these blue connections. Molecule 1 should stick to molecule 2, which should stick to molecule 8, et cetera. But there's always the potential for them to stick in a different way. So these red connections aren't actually being formed, but they could have been formed. So if the pieces come together in a different way, the red ones form a lattice, and the blue ones aren't being used. So that's a neural network connectivity pattern that corresponds to the molecular self-assembly pattern. And it gives a similar principle for how the system can work. So if we have a particular concentration of a certain pattern of concentrations of these units, say this one, molecule number 243, it could form in M over here, or it could be in A over here, it could be in H over here. Each molecule can appear in different places, but if the high concentration molecules happen to be co-localized in one of these shapes, what that means is it will be easier for these molecules to get together. They'll bump into each other more often. There'll be a reduced barrier to nucleation in this energy diagram if you make the H shape compared to if you start putting together pieces to make the other shapes where there's a high energy barrier. So essentially, this system will recognize or classify concentration patterns into H, A, or M based on where the high concentration molecules are co-localized. And then by deciding where we put our molecules in these shapes, we can essentially design a phase diagram such that when we train the system to recognize a specific set of patterns by putting the molecules, designing essentially the molecules to fit together with different co-localization patterns, we can design a system that actually recognizes the trained patterns and classifies them correctly. Here we have just 18 patterns. These are real experiments and experimental results, so this is not a big fancy system, but it does what it does. So that is a quick example of a kind of connection between neural networks and molecular self-assembly, where molecular systems can perform information processing like neural networks. A second example I'll show you very quickly is purely theoretical at this point, although there's a natural path to experimental implementation. And instead of pattern recognition, what we're focusing on here is pattern formation. specifically in reaction diffusion systems that I'm calling neural reaction diffusion systems. So this is work by my graduate student, Salvador Buse. So the idea is to have a reaction diffusion system, which I'll describe in a minute, where if you start with a little blob of chemicals in a dish, they will start turning each other on and off, so as to create a particular pattern that you trained the system to build. And this idea is basically adapting ideas from Mordvintsev et al. To the reaction diffusion context. So what is a reaction diffusion system? You have some chemical species, maybe 100 of them. There's some reactions between them, and so there's dynamics for how the concentrations change over time based on what those reactions are. And there's diffusion, where in a given spatial location, it diffuses to neighboring areas and might stimulate the neighboring areas to do something. Alan Turing actually really initiated the idea of reaction diffusion as the potential basis for morphogenesis. He was inspired by things like pufferfish patterns and spots and stripes on leopards and so forth, and showed that very simple chemical systems in the reaction diffusion constant can stabilize and make these kinds of interesting patterns. Here's a simulation of a reaction diffusion system called the Gray-Scott model. It just involves these two reactions, these two differential equations as a PDE in space. And if you tune the parameters, let's say the rate constant of this reaction and the rate constant of this reaction, you can tune it to regimes where it makes different kinds of patterns, either sort of blotches or stripes or dots. And so you can tune the system to make the pattern that you want as long as it's within the space of patterns that this system can make. So our question was, what if you want to make more complex patterns and you're willing to hypothesize that you can make a more complex chemical reaction network, which we think we can? There's actually methods to derive from an energy landscape. So here's an energy landscape that actually corresponds very closely to a neural network that Hopfield used for associative memories. And you can derive from this a set of chemical reactions, hypothetical chemical reactions, with hypothetical rate constants that are analogous to the weights in a neural network, such that the dynamics of this network, sort of as a well-mixed system, is exactly analogous to a modified form of the Hopfield network, essentially minimizing this energy function. So if you have a neural network sort of in a test tube, and now you ask, what if you spread it out in a big dish? What does this neural network do for pattern formation? You can simulate it by implementing these reaction diffusion equations with discrete space, discretized space, discretized time, say use Euler integration in a very simple way. And the standard equations that you would use can be exactly cast as a multi-layer neural network. One sort of time step corresponds to going from one set of concentrations to the next layer of the concentrations of all the species and all the locations, and then multiple steps correspond to multiple layers, so you have a deep neural network that is the reaction diffusion equations. So if you have that, then you can take an input pattern and a target pattern and a deep neural network that's a certain number of time steps of simulation, which will correspond to the number of layers in your network, do back propagation through time, and train your network, those weight parameters, the rate constants on the chemistry, so as to get the chemistry to do the pattern formation process from the given initial conditions. And so here's I think this is 64 by 64 example of training the network to make a lizard. So this kind of capability of reaction diffusion systems that wasn't previously clearly understood, the range of patterns that they can make, and I think here we have an argument that they can make essentially arbitrary patterns if you have enough species. Here there was about 100 species. It's also interesting that you can look at each species. So I think here's maybe 80 of them shown. And the different species now in the movie, you can see are doing different things. They're picking up on different kinds of spatial structures. And it's interesting to look at this because this is what biologists who look at gene expression, spatial patterns, what they see in their experiments, things that are sort of like this. OK, so since I started off talking about science and poets, I think I'm going to be willing to conclude by also making an extreme leap. But as you all are very aware, image generation is a very interesting thing that neural networks can be trained to do. And one of the ways the diffusion methods can start with essentially a random pattern, and then a structure forms out of it. We believe that reaction diffusion systems have the same capacity. If you had one with enough species, it would also be able to do the same kinds of things here. It's just we won't be able to make one with quite that many species. Not even close. So finally, I hope that this talk has given you at least some perspective on different ways to think about neural networks as a phenomenon of nature, and one that can be used for engineering molecular systems. Thank you.
Okay. All right. Thank you. Thanks, everyone. My name is Assad Oberai. I'm at the University of Southern California, but the plan is for me to be here for my sabbatical year next year, and hence the invite. Thanks to Anima and Andrew for inviting me to this workshop. It's been really interesting. I want to present some applications of machine learning, in particular deep learning in sustainability in healthcare. But given the time, I think I'll probably only cover sustainability. All right, so this is work that's been done by Brian Shaddy at my group, who's a graduate student, is here. Valentina is an undergraduate student. Deep Ray, who used to be my postdoc, is faculty at University of Maryland. And then other collaborators at San Jose State, University of Utah, and University of Colorado at Denver, where Jan Mandel is the lead. All right, so here we go. Okay, so we all live in California, and I think we all know that wildfires cause catastrophic damage, right? There's the direct damage that a wildfire causes, but there is obviously the indirect damage, which is basically health costs, shutdown of businesses, and then probably in the long run, closure of some businesses, right? So just to give you an idea of the amount of impact, the economic impact of wildfires, it's predicted that in California alone, in 2018, wildfires cost, the cost of wildfires was around $150 billion. That's about 0.7 of the US GDP, 0.7% of the US GDP for that year, right? So it's pretty significant. And if you look at the trend of what's happening in terms of wildfires in California, this yellow line is basically the 5-year average of the acres burnt in wildfires. And you can see it's sort of peaking up right about here, right? And that's due to this mega drought and the dry period that we've been having. And what's worse is this is not going to get any better, right? So climate change and sort of predictions based on climate change say that the US West Coast is going to have wetter winters, so there'll be more fuel created, and drier and hotter summers. There'll be more chance for this fuel to burn, right? Therefore, bad for wildfires, okay? So I think we can all agree that this is a problem that's going to stay. The question is, what can we do about it, right? So let's say you have a prediction tool that could actually predict the course of a wildfire. What would you do with it, right? So what you could do with it, of course, you could plan emergency response, right? So you could say, move this person out of here. you could plan firefighting response. So as a firefighter, you might say, put a fire break here, which is basically burn this part of the fuel before the fire gets there so that it doesn't go any further. And then, of course, you could deploy infrastructure more strategically, right? So all this is fine. So let's say we actually wanted to do this, right? So let's say you're now, you're in a position where you want to be able to predict the course of an active wildfire, right? What will it entail? So let's play out a scenario, okay? So as a scenario, what I'm going to look at is this fire which was in Texas. It's called the Vivian Fire, 2019. And what we know for this is, and we are at a point where we are like roughly about 40 hours into the wildfire, right? So it's already out there. So what do we know? What is all the data that's out there that we can make use of? Okay, so here is what we know. We know that it occurred about 40 hours ago, so we know roughly the ignition time, right? And then we have some satellite data. So this is satellite data that's been measured, and these are satellites that are orbiting the Earth, and so they go over that region sporadically, right? So at about 3 hours after ignition, there are these pixels which show active areas of wildfires. At about 25 hours, the satellite comes over it again, and here are some more pixels that show active areas, and then 27 hours, and then 39 hours, right? So these are active wildfire pixels that we have. So you can take all of this data, and you can put it together, and you can compute the arrival time, right? So what is arrival time? So this is basically you're sitting at a point, and you say, at what time did the wildfire get at this point post-ignition, right? And so we've non-dimensionalized time here. Ignition is 0, and 1 represents 48 hours. So this is early times. So it got here early, right? And then after that here, and then after that finally somewhere here, right? So this is the data. This is the total data that we have sitting at t equals 40 hours, and we now want to predict the course of this wildfire, all right? So obviously, this is not enough. What we also need is a predictive model. So what are the types of predictive models that are out there? So this is data, model, and later I'm going to use machine learning to combine data and model, right? So the data part is over. Let's move over to models. Okay, so turns out there is a lot of predictive capability to do wildfire modeling, and these are sort of, the 3, I would say, top tools that are out there. WRF-S-Fire, which is the one that we work with, QuickFire, which is a tool developed by the DOE, and Wi-Fire, which is used by folks at UCSD in San Diego, right? What you can say about all these tools is that if they're any good, they have to couple a fire spread model with a weather forecasting model, or with a model that models the atmosphere. And why is that? Because, as you probably well know, wildfires create their own weather, right? So they affect the weather. There is a coupling. Obviously, weather affects what happens to a wildfire, but what happens to weather is affected by wildfires, right? So there's got to be a coupled model. And so the model that we use is called WRF-S-Fire, and I'll take a second to show you one simulation from WRF-S-Fire. Here we go. So this is a simulation of the Caldor fire, which happened about 1.5 years ago, south of Lake Tahoe. And Lake Tahoe is somewhere up here, and this is the region that is south of Lake Tahoe, and this is going to play in a loop. The size of this domain is about, I think, 30 miles across, or maybe 40 miles across. So this was a big wildfire. And what's being shown here, the red area is basically the part that's been burned. The yellow part, yellow line here, or the yellow contour, is the part that's burning, right? You can see the wind vectors. These are the wind vectors at the surface, which are, of course, changing. And the time interval, right, going from 0 to whatever, 16 seconds, represents roughly about 1.5 days. So this is a simulation for 1.5 days. And if you pay close attention, you will see up here, you will see it actually expands a lot in that direction. So at time t equal to 0, the front is here, but by the time time reaches 2.16 seconds, right, it'll be all the way here. So that represents about 1.5 days worth of growth of this fire, right? So this is the kind of prediction that WRF-S-Fire or models like WRF-S-Fires can do, all right? So let's come back here, and let me carry on. Okay, All right, so this is what they can do. What are they comprised of? So WRF S-Fire has two parts. It has a model called S-Fire, and what this does is it basically predicts the growth of the wildfire on the surface. So it's a level set-based model, and the 0 level set tells you the perimeter of the fire, and given the perimeter at time t, it calculates the perimeter at time t plus delta t, and it does that based on a rate formula, which is semi-empirical, and it depends upon the terrain, it depends upon the fuel type, the surface winds, moisture, and temperature, all right? So that's S-Fire. But that's coupled to WRF, which is a weather prediction model, and that basically solves for conservation of mass, energy, balance of linear momentum, basically Navier-Stokes, right? And tells you the velocity, pressure, temperature, and moisture fraction in the atmosphere, right? And of course, these models talk to each other, right? So what happens? S-Fire, which is down here, gets from WRF the surface winds and temperature and moisture, and it calculates the spread or the growth of the wildfire, right? When the wildfire grows, it dumps a lot of heat and mass into the atmosphere, and those heat and mass fluxes go into WRF, and this cycle repeats itself. And so this is how these models are coupled with each other, all right? And this goes on. Okay, so I've now told you about the models, right? I told you about data, I told you about models. Let's come back to the problem that we were trying to address, right? So I have this data, which is the arrival time data for the Vivian fire, and I have my model, which is WRF S-Fire, and now I want to run it, right? I want to start at time t equals 40 hours, and I want to go further. So what do I need? What I need is a good initial state to start from, right? I need a good initial state to start WRF S-Fire from. What does that mean? What I need is a high-resolution fire perimeter at time t equals to 40. I need to know where the fire is at that time, and I need a good initial state of the atmosphere. By initial, I mean at time t equals 40 when all the heat has been dumped into the atmosphere, right? That's what I'm trying to get at. Okay, so how will I ever get that, right? So the key observation here, and this is really critical, is that if, this is a coarse and really coarsely sampled arrival time map, right? Imagine if I had a finely sampled arrival time map, right? So if I knew how the fire progressed between time t equals 0 to time equals 40, right, 40 hours, on a really fine resolution, what I could do is I could take that, play that in S-Fire, right? Just instead of computing the trajectory of the wildfire, I would prescribe the trajectory of the wildfire, and then S-Fire would put the right amount of heat fluxes into WRF, into the weather forecasting model, and at time t equals 40, I would have the correct initial condition for the atmosphere, right? So this is the key observation. The key observation is what I need is, what I have is this coarsely sampled arrival time. What I need is a finely sampled arrival time, right? Because if I have that, I know the fire perimeter at time t equals 40, and I know the right initial state of the atmosphere, right? So that's basically the inference problem we want to solve. The problem we want to solve is, given the sparsely sampled arrival time, phi bar, determine the finely arrival sample time, phi, over that time interval, right? And that's great. I can go back here, and I can start filling this up or smoothing it or interpolating it in some random way, but that's not the right way to do it, right? Because all of this is constrained by physics. So I also want to put the physical constraint in there, and I want to put in any prior knowledge that I might have. And so the right way to do this is set it up as a Bayesian inference problem and try and infer the finely sampled arrival time, right? Of course, this is a really challenging inverse problem or a Bayesian inference problem. Why? Because the quantity we want to infer is large dimensional, right? So this fire grid has at least 10,000, sometimes a million cells, and I want to find the arrival time on all of these cells. So this is a hard inference problem. And the prior knowledge that I have, which is all the physics, is really hard to sort of encode into a distribution, into a prior distribution, right? So how do we do this? So this is where machine learning comes in, right? We use a particular type of machine, a deep learning, probabilistic deep learning tool called a conditional generative adversarial network, which was developed by Adler, and then we worked on it some more. And what it does is, basically, it sort of treats phi bar and phi, the coarsely and the finely sampled arrival times, as random fields. And given lots of samples from the joint distribution of these two, it learns to sample from the conditional distribution. That is the conditional distribution of phi given phi bar, right? And what it relies on is the expressiveness of neural networks to learn the complex map that connects these two, the ability of GANs to learn from samples, right? Because we will have samples. We won't have explicit distributions. We will just have samples from the distribution. And it benefits from mapping this inverse problem into the latent space of the GAN, which is much lower dimensional than 10 to the power 4 or 10 to the power 6, right? So a quick slide on what this algorithm looks like, of what a conditional generative algorithm adversarial network looks like. You can sort of begin with this circle here. So what we have here is phi and phi bar, right? So we have lots of samples of the coarsely and the finely sampled arrival times. You take the coarsely arrival sample times and bring them here and feed them to the generator and this random vector to the generator. And what it produces is an approximation to the finely sampled arrival time. And then you get a collection of those, right? And so these two are fed into a discriminator, which tries to tell them apart. But the generator tries to fool them. And in doing so, what the generator basically learns is the conditional distribution of phi given phi bar, all right? And so that's how this works. And I'll give you a few examples of what the training samples look like, right? So how do we generate the training samples? The way we generate the training samples is we assume a flat terrain, vary the ignition point, vary wind speed and direction, and solve that problem using VRF fire, right? And so what I'm showing you here is an arrival time, which is finely sampled. In this case, the wind speed is very small, so the fire doesn't really spread at all. But if you look at this one, for example, right, it has a very high wind speed, and it's blowing in this direction. And so the fire sort of stretches out in this direction, and you can see the arrival time. So we take this, apply the measurement operator to this, and we get the coarsely sampled arrival time, right? So we generate lots of pairs like this, right? These are synthetic examples. So this is not real data. The model is going to be trained on data that's generated by VRF fire, right? Not on true experimental data. So we do about 10,000 such samples and train the model. And once the model is trained, right, what it takes as input is phi bar, the coarsely sampled arrival time for the Vivian fire, which is what this is, right? We feed it to the generator, and it produces an ensemble of possible, likely arrival times on a much finer grid, which is what this is. So you can sort of see it fills in the spaces basically based on whatever it has learned on what we trained it on, right? So we take 200 of these and compute the mean arrival time. And you can see this has a nice smooth structure. This tells you that the fire started somewhere here. Clearly, the wind was blowing in this direction. And so it sort of started to progress in this direction. There was a rapid growth that went from here to here, right? And then it sort of, stabilized. Since we have lots of samples, we can calculate or quantify uncertainty. So we can calculate the standard deviation in the arrival time. And that's what this is, right? And then we can validate what we computed against a fire perimeter that was measured a little bit after our prediction ended, right? So you can see this is an actual true measured fire perimeter, the black curve, and our sort of arrival time is right in the middle of it, right? And so the fire burnt a little bit more between here and here, and then it was put out, okay? So this is basically an approach with which we can sort of use the data that's available right now, use these predictive models, and then come up with the appropriate initial condition, which can then be used to initialize any fire prediction model, all right? So I think I'm done. So where are we right now? Looking ahead, what we want to do. We want to account for other measurements. And what do I mean by that? So what I showed you earlier, right, was a measurement from a satellite that is not geostationary. The advantage of having a geostationary satellite is it is constantly viewing the wildfire, right? The disadvantage is it measures on a much coarser spatial scale. The spatial scale is about 2 kilometers. So this is what a geostationary satellite is able to measure, right? So these are fires that are ongoing right now in Chile. There is like a huge wildfire season in Chile right now. And you can sort of see the extent of these fires because this is the entire width of this part of Chile, which is about, I think, 250 miles. And so, this region here is, 100 miles across and maybe 250 miles in north-south extent, right? So this is the scale of these wildfires. The data that is being measured here, right, is on a really sort of fast temporal scale. So I think every half an hour or 1 hour, you can get an image. But the spatial scale is very coarse. It's about 2 kilometers, right? So, but the point is, it can still be used in the approach that we're using. So you can sort of combine this heterogeneous data, one which is very finely sampled in space, and the other which is very finely sampled in time, and try and make better predictions. So that's one of the things that we're hoping to do. All right. So let me just sort of end here and say that, and say that there are sort of several interesting areas to sort of go further. One is that I think the network that I showed you isn't technically an operator network because it's mapping vectors to vectors, but it can be transformed, it can be changed to make it an operator network so it maps functions to functions. That's relatively easy to do. And then there are sort of improvements in the probabilistic part of it that can also be done. And there are lots of applications of this, in particular in healthcare, that my group is looking at. But that's topic for another time. So thank you very much.
So I have a question for Erik. So early on, you mentioned kind of flipping AI4Science on its head and predicting that someday we'll have an artificial cell. I'm curious if you think, maybe separately for that or prerequisite to that, if you think we'll also have a numerical model for a cell or some kind of simulation for a single cell, and whether that aligns with the perspectives we've seen all day of basically trying to model multi-scale dynamics. Isn't a cell moving over time a multi-scale dynamical system? I'm curious what your thoughts are on that.
I certainly don't have the answers, but I'm willing to embarrass myself by speculating. I think when one thinks about designing engineered things as opposed to the science of trying to understand existing biological things, there's some different factors in play. So building computers, one's able to employ things like design rules in how you sort of put your components together so as to make them predictable. And we couldn't build computers like we have right now without sort of limiting the way we put things together using uniform components like transistors and so forth, which avoid a lot of the, or fail to take advantage of a lot of the really clever things that electrons and silicon can do if we had fabricated really crazy devices. But we don't have good predictive models for building such things reliably. I anticipate that in the molecular world, there will similarly be layers of abstraction and design rules that you need to follow to build your molecules in certain ways that are restrictive. Means you have to make things not as fancy, not as sophisticated as biology, but allow one to scale up the complexity more robustly to make systems, cell scale, having millions and millions of components that are working together. So I think in order to achieve the artificial cell or artificial molecular robot vision, one doesn't need to solve all the problems that a biologist needs to solve in order to model, say, protein functions or molecular machines.
Thanks.
Hi, I also have a question for Erik. I'm not sure if this was answered, but in the section where kind of the molecular structures were forming shapes H, A, and M. I'm curious to get a picture of how the training actually works, like how we have that sort of memory for when they know how to form the shapes.
Yeah, I glossed over that because it usually takes a while to explain. What's essentially going on there is we're taking a design and we're saying, for the set of training images, we have, let's say, there's going to be a molecule that corresponds to a concentration number 1, another molecule that corresponds to concentration number 2, et cetera. And the question is, where in the shape should that molecule be? And it's basically going to be such that the high contrast, the white pixels in images that are supposed to be H, are going to end up co-localized in shape H, but spread around randomly in the other 2 shapes. So it's deciding that map of chemical species to location in the shapes that's the training process. And we weren't able to cast that as a gradient descent type backpropagation neural network thing. We used a brute force optimization that was essentially hill climbing on a physical model of nucleation.
Okay, I think that makes sense. Thank you.
Hi, my question is for Professor Oberai. I'm curious about the choice. First of all, first question is about wondering if you could speak to the multimodality of this coarse to fine distribution that you were predicting. And in line with that, I was curious about the choice of using a CGAN as opposed to something like a diffusion model. To what extent can this problem be framed like as an in-painting problem, and perhaps like a generation based on classify free gradients? Because I imagine the reverse problem going from fine to coarse is just a sampling. It could be framed differentiably as well. So what's the motivation for an adversarial loss there?
Yeah, that's a good question. You're absolutely right. I mean, to some extent, it is an in-painting problem. You're filling in, you're filling in parts where you don't have enough information, and of course, the parts where you have information are also noisy, right? They're sort of coarsely sampled, and they're probably noisy, and so the thing to do would be like whatever seems or is a good model to solve in-painting is probably a good model for this too. And so sort of diffusion-based models are certainly, worth trying. It's just that we haven't gotten to it. We've sort of been using conditional GANs to solve inverse problems for a while. We know how to do it well. We sort of understand the architecture. And we also know how to sort of transform those from sort of maps from one vector to another to maps from function to a function. So that's sort of our preference to do that. But so diffusion-based models are perfectly legit choice for this too.
Okay, thank you so much, Professor.
Sure.
Is it potentially an issue that you are using, this is for Assad, for your training data for your GAN, you are using simulations from the very same model that you're then trying to incorporate, and so that rather than using real data pairs, and so you might have well, it sort of reminds me a little bit of the inverse crime. So you might sort of just be learning too much of your own synthetic data.
An inverse crime. It might be an inverse peccadillo, because I think what we are doing is we are using our numerical model, which may be flawed, right, to come up with an initial condition, and then use that initial condition in the same numerical model, right? But when we use it, once the GAN is trained, we are using it on real data, right? So there is that. So it isn't exactly, I think, an inverse crime. Having said that, if we had lots of data of finely sampled arrival time and coarsely sampled arrival time, we would simply use it. There is no doubt about it. But the sort of finely sampled arrival time doesn't exist. Doesn't exist in terms of experimentally
measured, right? That doesn't happen. So we simply don't have it. So the training has to be done using some sort of a numerical model. One way to maybe amortize the risk is to use multiple models, an ensemble of models, right? Use quickfire, use Wi-Fire, and then use those results. So hopefully you're sort of combating the error that way.
All right, thank you.
Yeah.